Hello and welcome back. I'm glad you're here. Tonight we're going to explore one of humanity's oldest and most profound questions. A question whispered under ancient skies and now asked with radio telescopes pointed toward distant stars. Are we alone? Could there be life, perhaps even civilizations, somewhere out there in the cosmic dark? This isn't a journey of definitive answers. It's something gentler than that. We'll wander through what we know, what we're searching for, and what we've imagined. We'll visit frozen moons with hidden oceans, listen to signals that traveled for decades through empty space, and contemplate why, in a universe so vast, we seem to hear only silence. If you haven't already, consider subscribing to the channel. It helps us continue creating these quiet explorations together, week after week, as we drift through the mysteries of the cosmos. Get comfortable. Let the weight of the day settle. There's nowhere you need to be, nothing you need to solve. Tonight we're simply here, looking up together, wondering what might be looking back. Now let's begin the scientific search for extraterrestrial intelligence, known by its gentle acronym SETI, officially began in 1960. That's when an astronomer named Frank Drake, working at the National Radio Astronomy Observatory in Green Bank, West Virginia, pointed an 85-foot radio telescope toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani. He called it Project Ozma, after the queen of the fictional land of Oz. Perhaps there was something hopeful in that choice, something that acknowledged both the fantastic nature of the search and the possibility that, like Dorothy, we might find something real beyond our own world. Drake listened for just a few months. He searched at a single frequency, 1420 megahertz, the natural broadcast frequency of hydrogen, the most abundant element in the universe. He heard nothing conclusive, no voices from the void, no mathematical sequences that couldn't be explained by natural phenomena. But that didn't matter, not really, because in those months of patient listening, something fundamental changed. The search for alien life transformed from the realm of science fiction into the realm of science itself. Drake had proven it could be done, and once something can be done, it begins to feel inevitable that eventually someone will succeed. On August 15th, 1977, a volunteer at Ohio State University's Big Ear Radio Telescope was reviewing computer printouts of data collected during the night. The telescope had been automatically scanning the sky, recording radio signals from different patches of space, moving methodically like a slow reader working through pages of cosmic text. And there, in the columns of numbers, something appeared that made him grab a red pen and circle the sequence, writing a single word in the margin. Wow. The signal lasted exactly 72 seconds, the length of time it would take for Earth's rotation to sweep the telescope's beam past a fixed point in space. It came from the direction of Sagittarius, deep in the heart of our galaxy, and it arrived at 1420 megahertz. That same hydrogen frequency Drake had chosen 17 years earlier, the frequency scientists had long predicted aliens might use to announce themselves across the interstellar distance. We've never heard it again, not in decades of subsequent observations of that same patch of sky. Perhaps it was a one-time burst from some natural phenomenon we don't yet understand. Perhaps it was a reflection of our own technology bouncing back from space debris. Or perhaps, and this is the thought that keeps astronomers searching, it was exactly what it seemed to be: a brief hello from somewhere out there, transmitted once, never repeated, like a lighthouse glimpsed through fog that vanishes when you turn to look directly at it. We've done more than listen. We've also spoken, sending deliberate messages outward into the cosmic ocean, hoping someone might eventually wash ashore. The first was the Arecibo message, transmitted on November 16, 1974, from the Arecibo Observatory in Puerto Rico, at the time the largest radio telescope on Earth. Scientists had just upgraded the facility and wanted to demonstrate its power. So they composed a message, 1679 binary digits, that, when arranged in a specific rectangle, formed a pictogram containing information about humanity, our DNA, our solar system, and the telescope itself. They aimed it toward M13, a globular cluster containing 300,000 stars, about 25,000 light-years away. If anyone is there to receive it, the message will arrive around the year 26,974. If they reply immediately, we'll hear back around 51,974. The entire conversation will span 50,000 years, longer than recorded human history. We've sent 3 other deliberate messages since then, each a carefully crafted introduction. A cosmic, "Hello, we exist," thrown into an ocean so vast that even the speed of light feels impossibly slow. These messages drift outward even now, expanding away from Earth at 186,000 miles per second, carrying the dreams and mathematics of a species that couldn't bear the thought of never being heard. The word astrobiology sounds modern, technical, like something invented for space-age science, and in a sense, it was. The term only came into widespread use in the 1990s, when NASA established its Astrobiology Institute, formalizing the study of life's potential throughout the universe. But humans have wondered about life beyond Earth for millennia. Ancient Greek philosophers debated whether the moon and planets might be inhabited. Medieval scholars pondered whether God would have created only one world bearing life. Every culture that looked up at the night sky and told stories about the stars was, in some way, asking the question. What changed in the 1990s was the science. We finally had the tools to investigate seriously. The combination of biology, chemistry, astronomy, geology, and atmospheric science converged into a single, contemplative field. Astrobiology is the study of life's origins, its evolution, its future, and its distribution throughout the cosmos. It asks, what is life? How does it begin? Where might it exist? And perhaps most intriguingly, would we recognize it if we found it? It's a field built on one profound assumption, that Earth is not unique, that the story of life here might be repeated, with variations, on countless worlds we'll never see. And every discovery, every new exoplanet, every extremophile bacteria found thriving in impossible places on Earth adds another verse to that hypothesis. There are more stars in the universe than grains of sand on all of Earth's beaches. Think about that for a moment. Every beach you've walked on, every shore where waves break against continents, every hidden cove and vast desert coastline. Count every grain of sand from all of them combined, and the stars outnumber them. The current estimate sits around 200 billion trillion stars. That's a 2 followed by 23 zeros, a number so large it stops feeling like a number at all, and becomes instead a kind of invocation, a mathematical prayer to vastness. And here's what makes it even more staggering. Most of those stars host planets. Not all, but most. Planets seem to be the rule rather than the exception, which means the universe contains not just stars, but worlds. rocky worlds, gas giants, ice worlds, worlds we don't have names for yet. Uncountable stages where the drama of matter might unfold into something like life, might organize itself into systems that metabolize, reproduce, evolve. The universe has had 13.8 billion years to experiment. It's had countless laboratories, near infinite raw materials, and the patience of deep time. If life arose here, on this one particular rock orbiting this one particular star in the outer spiral arm of one particular galaxy among hundreds of billions of galaxies. Well, the mathematics alone suggest we're likely not the only time the universe looked back at itself and wondered. Around every star, there's a region, not too hot, not too cold, where a rocky planet with the right atmosphere could maintain liquid water on its surface. Scientists call it the habitable zone. Everyone else calls it the Goldilocks zone, after the fairy tale about the porridge that was just right. For our sun, this zone extends roughly from Venus's orbit to Mars's orbit, with Earth sitting comfortably in the middle. If you move inward, you get Venus, a runaway greenhouse where lead melts on the surface. Move outward and you get Mars, a frozen desert where water exists mostly as ice. But here's what we've learned as our telescopes improved and our understanding deepened. Habitability is far more complex than temperature alone. You also need the right kind of star, not too violent, not too short-lived. You need a planet with a protective magnetic field to shield life from cosmic radiation. You need plate tectonics to recycle minerals and regulate atmospheric carbon dioxide over geological time. You might need a large moon to stabilize the planet's axial tilt, preventing wild climate swings. Perhaps you need a Jupiter-like planet in the outer system, acting as a gravitational vacuum cleaner, deflecting comets that might otherwise bombard the inner worlds too frequently for complex life to gain a foothold. The Goldilocks zone is real, but it's also just the beginning, a first filter, a necessary but not sufficient condition. It tells us where to look, but not whether anyone is home. In 1995, astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, the first confirmed planet orbiting a sun-like star. It was a strange world, a gas giant larger than Jupiter, but orbiting closer to its star than Mercury orbits our sun, completing a year in just 4 days. The discovery turned planetary science on its head. Everything we thought we knew about how solar systems form had to be revised. That was less than 30 years ago. Today we've confirmed the existence of over 5,000 exoplanets, with thousands more candidates awaiting verification. The pace of discovery has been breathtaking. What was once impossible, finding worlds around distant stars, became merely difficult, then routine, then automated. We've found planets made of diamond. We've found planets where it rains glass sideways. We've found planets orbiting binary stars, giving them double sunsets. We've found rogue planets drifting between stars with no sun at all. We've found planets so close to their stars they're being evaporated, leaving comet-like tails of atmosphere streaming behind them. And among these thousands of worlds, we've found dozens of rocky planets orbiting in their stars' habitable zones. Worlds where, if you could stand on the surface, you might look up at an alien sky and watch clouds drift past an unfamiliar sun, just as we do here. The universe, it turns out, is abundant with worlds. The question is whether any of them are abundant with life. In 1961, Frank Drake, the same astronomer who conducted that first search the year before, was organizing the first SETI conference. He wanted an agenda for the meeting, a framework to structure the conversation. So he scribbled down an equation that attempted to estimate the number of communicative civilizations in our galaxy. It looks like this: N Hu R X FP X NE X FL X Phi X FC XL. Each variable represents a step in the cosmic journey from stars to conversations. R is the rate of star formation. FP is the fraction of stars with planets. NE is the number of planets per star that could support life. FL is the fraction where life actually arises. Phi is the fraction where life becomes intelligent. FC is the fraction that develops technology we could detect. And L is the length of time such civilizations broadcast detectable signals. Drake never intended it as a serious tool for calculation. Most of the variables were complete unknowns in 1961. It was meant to stimulate discussion, to break down an impossibly large question into smaller, more manageable pieces. The fascinating thing is how much has changed. We now have solid numbers for the first 3 variables. We know how often stars form. We know that planets are common. We're beginning to understand how many planets sit in habitable zones. But the last 4 variables, the ones involving life itself, remain mysteries. We have exactly 1 data point: Earth. And from a single example, you can't determine what's typical. The Drake equation remains what it always was: not a prediction, but a prayer, a hopeful map of the territory between here and contact. One of the most intriguing facts about life on Earth is how quickly it appeared. Our planet formed about 4.5 billion years ago. For the first few 100 million years, it was a hellscape. Bombarded by asteroids, volcanic, with an atmosphere of methane and ammonia, far too hot for liquid water. But by about 3.8 billion years ago, maybe earlier, life had already emerged. The oldest fossils we found, microscopic structures preserved in ancient rocks, date to about 3.5 billion years. Geochemical signatures in even older rocks suggest life might have been present 3.8 or even 4 billion years ago. Think about what that means. Almost as soon as Earth was cool enough, stable enough, wet enough to support life, life appeared. It didn't take billions of years of lucky chemical accidents. It took at most a few 100 million years, which on geological timescales is almost immediate. This impatience, this apparent eagerness of life to begin, suggests something profound. Either life arises easily wherever conditions permit, or Earth got fantastically lucky very early. If it's the former, the universe might be teeming with biology, and our silence might indicate we're searching wrong, looking for the wrong signals, listening at the wrong frequencies. If it's the latter, we might be more alone than we ever imagined. The product of a chemical miracle so improbable it's happened only once in the entire observable universe. We don't know which it is, but the speed with which life took hold here makes one truth clear. Wherever the chemistry is right, wherever energy flows and atoms can combine in complex ways, life at least tries to happen. And trying, as they say, is half the battle. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. These 6 elements, often abbreviated as SECHNOPS, form the chemical backbone of all life on Earth. They're what your DNA is made of, what your proteins fold from, what your cells use to store and transfer energy. Here's the wonderful thing. These elements aren't rare. They're among the most abundant elements in the entire universe. Hydrogen is everywhere, It's the universe's favorite element, making up about 75% of all normal matter. Carbon forms in the hearts of aging stars and gets scattered into space when those stars die. Oxygen is the ash of helium fusion. Nitrogen emerges from massive stars. These elements drift through space in vast molecular clouds, clumping together, forming complex organic molecules even in the cold emptiness between stars. Astronomers have detected amino acids in meteorites, the building blocks of proteins, delivered to Earth from space. We've found sugars in interstellar clouds. We've detected alcohol molecules, not just simple ethanol, but complex organic chemistry, floating in regions where new stars are forming. The universe is, in a very real sense, chemically prepared for life. The library is stocked. The ingredients are available everywhere. If you need carbon to build complex molecules, there's carbon. If you need water as a solvent, hydrogen and oxygen are abundant. The cosmic chemistry is permissive, even generous, which raises the question, if the ingredients are everywhere, and they naturally combine into increasingly complex molecules, why don't we see life everywhere? Or perhaps we do, and we just haven't learned to recognize it yet. Perhaps the universe is whispering its presence in languages we haven't learned to decode. For most of human history, we assumed life needed gentle conditions. Moderate temperatures, clean water, plenty of sunlight, stable chemistry. And then we started looking more carefully at Earth, and we found life thriving in places that should, by all reasonable expectations, be sterile. There are bacteria living in the boiling acidic hot springs of Yellowstone, where the pH is lower than battery acid, and the temperature approaches that of boiling water. There are microbes in the frozen lakes beneath Antarctica's ice sheets, where no sunlight has penetrated for millions of years, and the water is colder than your freezer. There are organisms living miles beneath the ocean's surface, in the crushing darkness of hydrothermal vents, where the water is superheated by volcanic activity and laced with chemicals that would be toxic to most life. We've found bacteria inside nuclear reactors, happily metabolizing radiation that would kill a human in minutes. We've discovered microbes living in the incredibly salty waters of the Dead Sea and in rocks miles beneath Earth's surface, where they've been isolated from the surface world for millions of years. These extremophiles, lovers of extreme conditions, have fundamentally expanded our sense of what's possible. Every time we declare a place too hot, too cold, too acidic, too radioactive for life, we find something living there anyway, quietly going about its business of survival. And if life on Earth can adapt to such extremes, what does that say about the potential for life elsewhere? Maybe the frozen oceans of Europa aren't too cold. Maybe the methane lakes of Titan aren't too strange. Maybe the acidic clouds of Venus aren't too hostile. Life, it seems, is more creative, more persistent, more adaptable than we ever gave it credit for. Among all of Earth's extremophiles, few are as remarkable as tardigrades, tiny animals less than a millimeter long, with 8 legs and a peculiar lumbering gait that earned them the nickname water bears. These microscopic creatures can survive conditions that seem impossible. They've been exposed to the vacuum of space. No air, no pressure, cosmic radiation streaming through them, and they survived. They've been frozen to near absolute zero, just a few degrees above the coldest temperature theoretically possible, and they survived. They've been heated to 300 degrees Fahrenheit and survived. They've been exposed to radiation doses that would kill almost any other organism on Earth, and they survived. How? Through a process called cryptobiosis, a state of suspended animation where the tardigrade essentially pauses its biology. It expels almost all the water from its body, up to 99% of its moisture, and replaces it with a sugar called trehalose, which forms a glass-like substance protecting its cells. Its metabolism slows to 0.01% of normal. It's not quite alive and not quite dead. It's waiting. In this state, tardigrades can survive for decades, perhaps longer. We don't know the upper limit. When water returns, they rehydrate, and within hours they're moving again, feeding, reproducing, as if nothing happened. They've been here for over 500 million years, surviving every mass extinction Earth has thrown at life. And if something so complex, so multicellular, can endure conditions that we associate with the void of space, what might simpler organisms be capable of? Could life travel between planets on meteorites, frozen in rock, waiting for water? Could the galaxy itself be seeded with biology, drifting between stars on cosmic timescales? The tardigrade doesn't answer these questions, but it makes them seem less impossible. There's a pattern on Earth that's become increasingly clear as our ability to explore extreme environments has improved. Wherever liquid water touches rock, we find life. It doesn't matter if it's deep in the ocean, miles beneath the surface, in acidic hot springs, or in freezing Antarctic lakes. If water and rock meet and remain in contact for geological spans of time, life appears, or if it was already present, it persists. This isn't a small observation. It suggests that life doesn't need sunlight. Photosynthesis is only one strategy among many. It doesn't need organic-rich environments. Some bacteria can extract energy from chemical reactions with rocks alone. It doesn't even need access to the surface world or connection to the larger biosphere. Deep beneath the ocean floor, miles down in the porous rocks of the oceanic crust, there's an entire shadow biosphere. Microbes living off the chemical energy released when seawater reacts with hot rock. They've never seen sunlight. They've been isolated from the surface for millions of years. Yet they thrive, reproducing slowly in the dark, their metabolism ticking along at a geological pace. This has profound implications for worlds like Europa or Enceladus, where liquid oceans exist beneath thick ice shells. Those oceans sit on rocky mantles. Water touches rock. Hydrothermal chemistry likely occurs. If the pattern holds, if life really does emerge wherever this fundamental condition is met, then these moons might host their own shadow biospheres, entire ecosystems we've never imagined, living in darkness beneath alien ice. The universe might be full of places where water meets rock. And if Earth is any guide, those places might be full of life. In the deep rocks beneath Earth's surface, scientists have found bacteria that perform a kind of metabolism that seems almost like science fiction. These organisms don't eat organic matter. They don't perform photosynthesis. Instead, they extract electrons directly from minerals in the rock itself, using those electrons to power their cellular processes. It's called lithoautotrophy, literally self-feeding on rock. And it represents a form of life that's chemically independent of the sun. While most life on Earth ultimately depends on photosynthesis, which depends on sunlight, these bacteria have opted out of that entire chain. They found a different source of energy, the planet itself. They oxidize iron, manganese, sulfur compounds in rocks, pulling electrons from the mineral matrix and using those electrons the way we use the calories from food. It's a slow process. These bacteria live their lives at an almost meditative pace, dividing perhaps once a year or once a decade. But it works. It's sustainable. And it's been happening for billions of years. This opens up possibilities we rarely consider. Life might exist on worlds with no sunlight at all, rogue planets ejected from their solar systems, drifting in interstellar space. Life might exist deep in planetary crusts, miles below any surface, sustained entirely by geological chemistry. Life might exist in places so fundamentally different from what we imagine that we need to revise our entire concept of what an ecosystem looks like. The universe might be full of life we'd never think to search for, because it's not eating anything we recognize as food, not living anywhere we think to look. Every living thing on Earth uses the same genetic system. DNA stores information, RNA transmits it, and proteins execute the instructions. This universality is one of the strongest pieces of evidence that all life on Earth shares a common ancestor. We all use the same molecular language because we all inherited it from the same original source. But DNA and RNA aren't the only possible genetic molecules. They're just the ones that won the evolutionary race here on Earth billions of years ago. In laboratories, scientists have created artificial genetic systems, XNA, or xenonucleic acids, that can store information and evolve just like DNA, but with completely different chemical backbones. These synthetic molecules use different sugars, different bases, different chemical structures entirely. Yet they work. They can replicate, mutate, evolve. They can encode information and pass it to subsequent generations. They're not found in nature, not on Earth anyway, but they demonstrate that DNA isn't the only solution to the problem of heredity. This means that alien life might use completely different biochemistry. Its genetic code might be written in molecules we wouldn't immediately recognize as genetic material. It might not have DNA at all. It might have something analogous but chemically distinct, something that arose from that planet's unique chemical environment. When we search for life, we tend to look for the familiar: DNA, proteins, cellular membranes made of lipids. But life elsewhere might be built on entirely different molecular scaffolds, spelling out its heredity in chemical alphabets we've never seen. The challenge isn't just finding life, it's recognizing it when we do. Water is the universal solvent of life on Earth. It's liquid across a convenient temperature range. It dissolves a wide variety of molecules, and its chemical properties make it ideal for biochemistry. But water isn't the only liquid in the universe. Saturn's moon Titan has lakes and rivers and seas, not of water, but of liquid methane and ethane. It's the only other world we found with stable liquids on its surface. The temperature is frigid, about 290 degrees Fahrenheit, far too cold for liquid water. But at that temperature, methane remains liquid, and Titan's atmosphere rains methane down onto the surface, where it carves channels and fills lake beds, creating a hydrological cycle eerily similar to Earth's, but with entirely different chemistry. Could life exist in liquid methane instead of water? It seems almost absurd. Methane doesn't have water's versatile chemistry. Biochemical reactions would be incredibly slow at such low temperatures. What takes a second in water might take years in methane. But theoretical biochemists have explored the possibility, and the answer is maybe. Life in methane would be radically different. It would metabolize different compounds, store energy in different bonds, build its cellular structures from different molecules. It would be alien in a fundamental sense, not just unfamiliar, but operating on completely different thermodynamic and chemical principles. If such life exists on Titan, it would be living in slow motion from our perspective, its days stretching into what we'd experience as years. Its ecology would be frigid and strange, operating at the edge of what chemistry can accomplish, but it would still be life, organizing matter, reproducing, evolving, surviving in conditions we can barely imagine. Carbon is life's favorite element on Earth because it forms strong, stable bonds with itself and many other elements, creating the complex molecules, proteins, DNA, fats, sugars, that biology needs. But silicon sits directly below carbon on the periodic table, and it shares some of carbon's bonding properties. Could silicon serve as the backbone of alien biochemistry? The idea of silicon-based life has fascinated scientists and science fiction writers for decades. Silicon is abundant. It's one of the most common elements in Earth's crust. It can form long chains and complex molecules, at least in theory. But there are problems. Silicon-oxygen bonds are extremely strong and stable, so stable that silicon dioxide, sand, glass, quartz, is essentially inert. Carbon dioxide is a gas we exhale. Silicon dioxide is a rock. This makes silicon-based metabolism challenging to imagine. How would silicon life process and excrete waste products if those products are solid minerals? Silicon chemistry also becomes less versatile as temperature increases, whereas carbon chemistry thrives at the temperatures where water is liquid. For silicon-based life to work, it would probably need cold environments, perhaps worlds with liquid nitrogen, or planets where ammonia serves as the solvent. It's probably rare, if it exists at all. Carbon simply works better for almost everything biochemistry needs. But the universe is vast, and chemistry is flexible. In environments with abundant silicon and scarce carbon, in cold regions where silicon's chemistry is more stable, perhaps evolution has found solutions we haven't imagined. Perhaps somewhere, there are beings whose cells are built on silicon scaffolds, thinking slow, crystalline thoughts, dreaming dreams we'd never recognize. It's easy to forget that the atmosphere we breathe, 21% oxygen, perfectly calibrated for our respiration, is not Earth's natural state. It's an aberration, a chemical impossibility created and maintained by life itself. The earliest life on Earth emerged into an atmosphere with virtually no free oxygen. Those organisms were anaerobic. They metabolized without oxygen, extracting energy from sulfur compounds, iron, or organic molecules through fermentation. And to them, oxygen was toxic. It reacted violently with their cellular machinery, destroying the delicate chemistry that kept them alive. Then, about 2.4 billion years ago, something revolutionary happened. Cyanobacteria evolved photosynthesis, the ability to split water molecules using sunlight, releasing oxygen as a waste product. This oxygen began accumulating in the atmosphere, first reacting with dissolved iron in the oceans, then gradually building up in the air itself. This was the Great Oxygenation Event, and it was catastrophic for most life on Earth at the time. Oxygen, so essential to us, was a global poison. It caused a mass extinction, killing countless species of anaerobic bacteria. The survivors were those that either evolved mechanisms to tolerate oxygen or retreated to oxygen-free refuges, the deep ocean underground, the intestines of animals where they persist today. For alien life, this history suggests a profound possibility. What we need to survive might be lethal to them. What they breathe might kill us. Life doesn't have universal requirements. It has local adaptations. And the universe might be full of worlds where the atmospheres would seem toxic to us, yet to the natives, our oxygen-rich air would be the true poison. Life appeared on Earth about 3.8 billion years ago, simple, microscopic, surviving on chemical energy from rocks and dissolved minerals. But photosynthesis, the revolutionary ability to capture sunlight and turn it into usable energy, didn't evolve until roughly 2.8 billion years ago, perhaps later. That's a billion years. A billion years of life existing, evolving, diversifying, but doing it all in the chemical dark, powered by fermentation and chemosynthesis, never tapping into the abundant energy streaming down from the sun. Why did it take so long? Photosynthesis is complex. It requires sophisticated molecular machinery to capture photons, split water molecules, and convert that energy into chemical bonds. It had to evolve piece by piece, each component providing some incremental advantage, until finally the whole system worked together. But a billion years is a long time. It suggests that photosynthesis, or something like it, might not be inevitable. It might be difficult, rare, the product of specific evolutionary circumstances that don't occur on every planet. If this is typical, then many alien worlds might be in their pre-photosynthetic phase right now. They might host life, simple, microscopic, thriving in chemical niches, but they wouldn't have forests or oceans full of phytoplankton or vast ecosystems converting starlight into biomass. They'd be biologically active but chemically limited, waiting for that crucial innovation that might take another billion years to arrive. The universe might be full of life that's still waiting for its own revolution, still living in the chemical twilight before something discovers how to harness the stars. Life appeared quickly on Earth, within a few 100 million years of the planet becoming habitable. But multicellular life, organisms made of many cells working together, took far longer, about 3 billion years longer. For roughly 3/4 of Earth's biological history, life consisted entirely of single-celled organisms, bacteria, archaea, eventually eukaryotic cells with nuclei and organelles, but all single cells, floating alone or in loose colonies, never organizing into the complex structures we associate with animals, plants, or fungi. Then around 600 million years ago, something changed. Multicellular organisms appeared. First simple sponges and algae, then increasingly complex forms, eventually culminating in the Cambrian explosion about 540 million years ago, when nearly all major animal body plans appeared in the fossil record within a span of 20 to 30 million years. We don't fully understand what triggered this transition. Perhaps atmospheric oxygen finally reached levels that could support larger organisms. Perhaps genetic innovations allowed cells to specialize and coordinate. Perhaps ecological pressures, predation, competition, favored organisms that could grow larger and more sophisticated. But the timescale tells us something important. Complex life is hard. Multicellularity requires cooperation, communication between cells, specialized tissues, coordinated growth. These aren't simple problems to solve. If Earth's timeline is typical, then the universe might be full of planets hosting single-celled life, vast microbial oceans, bacterial mats, simple ecosystems persisting for billions of years. But animals, plants, anything we'd recognize as complex life, those might be rare. Most life in the universe might be microscopic, invisible from a distance, detectable only if we physically sample another world's water or soil. The cosmos might be alive, but still mostly simple, still waiting for complexity to emerge. Jupiter's moon. Europa is slightly smaller than Earth's moon, and from space it looks like a cracked egg. Its surface is pale ice, crisscrossed with reddish-brown fractures that stretch for hundreds of miles. But beneath that frozen shell lies something extraordinary, an ocean of liquid water. This ocean is global, covering the entire moon beneath ice that might be 10 to 15 miles thick, and it's deep. Estimates suggest it could be 40 to 100 miles deep, which means Europa contains roughly twice as much water as all of Earth's oceans combined. That's an almost incomprehensible amount of liquid water hidden in perpetual darkness beneath the ice. What keeps it liquid? Europa orbits Jupiter in an elliptical path, and as it does, Jupiter's immense gravity squeezes and flexes the moon, generating tidal heating. This constant flexing warms Europa's interior, keeping that vast ocean from freezing solid, despite being so far from the sun that temperatures on the surface hover around 260 degrees Fahrenheit, where there's liquid water in contact with rock, and Europa's ocean likely sits atop a rocky mantle. There's potential for the chemistry that supports life. Hydrothermal vents might exist on Europa's ocean floor, similar to those on Earth, releasing minerals and heat into the dark water. And if Earth's pattern holds, if life really does appear wherever water touches rock, then Europa might be inhabited. We wouldn't find forests or fish. If life exists there, it would be microbial, perhaps forming mats around hydrothermal vents, living in total darkness, sustained by chemical energy from the moon's interior. But it would still be life, a second independent origin of biology in our own solar system. And that discovery would change everything we understand about our place in the universe. Saturn has over 80 moons, but one of them, Enceladus, a tiny ice world just 300 miles across, has captured scientists' imaginations like few other objects in the solar system. Because Enceladus is actively shooting water into space. In 2005, the Cassini spacecraft flew past Enceladus and discovered enormous geysers erupting from cracks near its south pole. These plumes shoot water vapor and ice particles hundreds of miles above the surface, some of it escaping the moon's weak gravity entirely, contributing to one of Saturn's rings. But here's what makes it remarkable. Cassini flew directly through these plumes, sampling their contents. The water contained salt, suggesting it comes from a liquid ocean. It contained organic molecules, carbon-based compounds, the building blocks of life. It contained molecular hydrogen, which forms when hot water reacts with rock, exactly the kind of chemistry that could provide energy for microbial life. Enceladus has essentially invited us to sample its ocean without even landing. The plumes bring ocean water directly to space, where we can analyze it. Future missions could fly through these geysers repeatedly, collecting samples, searching for more complex organic molecules, perhaps even looking for signs of metabolism or cellular structures. This tiny moon, smaller than the state of Arizona, might host one of the solar system's most accessible environments for life. We don't even need to drill through miles of ice. Enceladus is generously offering us sips of its hidden ocean, as if eager to share its secrets. The Mars we see today is a frozen desert, rusty red, dry, with an atmosphere so thin it's nearly a vacuum. The average temperature hovers around 80 degrees Fahrenheit. Any liquid water would immediately either freeze or evaporate. It's a harsh, seemingly lifeless world. But Mars wasn't always this way. About 3.7 billion years ago, Mars was warmer and wetter. Spacecraft orbiting Mars have mapped ancient river valleys carved into the landscape, deltas where rivers once emptied into standing bodies of water, and geological evidence of what might have been a northern ocean covering much of the planet's lowlands. This wasn't a brief period. The evidence suggests Mars maintained liquid water on its surface for hundreds of millions of years, perhaps longer. That's more than enough time for life to arise if the chemistry was favorable. Earth's life appeared within a similar time frame. What happened? Mars is smaller than Earth, so it cooled faster. Its interior solidified, shutting down the magnetic field that had protected its atmosphere from the solar wind. Over millions of years, the sun's radiation stripped away Mars's atmosphere, lowering the pressure until liquid water could no longer exist on the surface. The planet dried out, froze, became the desert we see now. But if life arose during Mars's warmer period, it might not have gone extinct. It might have retreated underground, following the water as it sank deeper into the planet's crust. There might still be liquid water miles beneath Mars' surface, kept from freezing by geothermal heat. And in that water, ancient Martian microbes might persist, descendants of a biosphere that once thrived beneath wetter skies. Venus is Earth's closest neighbor, similar in size and composition, sometimes called Earth's twin. But where Earth is lush and temperate, Venus is hell. Its surface temperature is hot enough to melt lead. Its atmospheric pressure is 90 times greater than Earth's, and its clouds are made of sulfuric acid. No water exists on the surface. It all boiled away long ago. Yet Venus might not have always been this way. Climate models suggest that for perhaps 2 or 3 billion years after its formation, Venus could have been habitable. It might have had liquid water oceans, a moderate climate, conditions not terribly different from early Earth. What went wrong? Venus is closer to the Sun than Earth, just 28% closer, but that was enough. As the Sun gradually brightened over billions of years, Venus crossed a tipping point. Water began evaporating faster than it could condense. Water vapor is a greenhouse gas, so this warmed the planet further, evaporating more water, creating a runaway effect. Eventually, the oceans boiled away entirely. Ultraviolet light from the sun split the water molecules, and the hydrogen escaped to space while the oxygen reacted with rocks. What remained was the scorched world we see today. But for those first 2 or 3 billion years, if Venus was indeed habitable, life might have emerged. And when the runaway greenhouse began, perhaps some organisms adapted, retreating to niches that remained temperate. Even today, high in Venus's atmosphere about 30 miles up, the temperature and pressure are surprisingly Earth-like. Some scientists speculate that microbes might persist there, floating in the clouds, living in droplets of acid, descendants of a biosphere that fled upward as the surface became uninhabitable. The nearest star to our Sun is Proxima Centauri, a small red dwarf about 4.2 light years away. In cosmic terms, it's practically next door, though next door still means the light we see from it tonight left that star over 4 years ago, and any spacecraft we currently possess would take tens of thousands of years to reach it. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri. They named it Proxima Centauri b, and it immediately became one of the most intriguing worlds beyond our solar system. It's roughly Earth-sized, perhaps 1.3 times Earth's mass, and it orbits in the habitable zone of its star, the region where liquid water could exist on the surface. There are complications, of course. Proxima Centauri is a red dwarf, cooler and dimmer than our Sun, which means the habitable zone is much closer to the star. Proxima b orbits its Sun every 11 days, far closer than Mercury orbits our Sun. At that distance, it's probably tidally locked. One side always faces the star, the other in perpetual darkness, like our Moon's relationship with Earth. Red dwarfs are also temperamental. They produce powerful stellar flares that could strip away a planet's atmosphere or bombard the surface with radiation. Whether Proxima b could maintain an atmosphere, whether it has water, whether it could support life, these remain open questions. But it's there. The nearest star to our Sun hosts a potentially habitable planet. If we ever develop the technology to send probes to other star systems, this will likely be humanity's first target, a world we could reach, theoretically, with sufficient determination. And knowing it's there, knowing that possibility exists so close, makes the universe feel less vast and more inviting. Our Sun will last about 10 billion years before exhausting its hydrogen fuel and expanding into a red giant. That sounds like a long time, and it is. Earth has already existed for roughly half the Sun's lifespan. But compared to red dwarf stars, our Sun is almost ephemeral. Red dwarfs are the most common type of star in the galaxy. About 75% of all stars are red dwarfs. They're small, dim, cool, and they burn their fuel with extraordinary efficiency. A red dwarf can continue fusing hydrogen for hundreds of billions of years, even trillions of years, depending on its mass. This means that planets orbiting red dwarfs have vastly longer timescales for evolution than Earth had. If life on Earth took 3.8 billion years to go from simple cells to human civilization, imagine what might evolve given 100 billion years, or 500 billion years, or a trillion years. The possibilities become almost difficult to conceptualize. Of course, there are challenges. Red dwarfs produce less light, so habitable zones are closer to the star, raising issues with tidal locking and stellar flares. But if life can overcome these obstacles, and extremophiles on Earth suggest it might, then red dwarf planets could host the oldest, most evolved civilizations in the galaxy. By the time our Sun dies, any life on red dwarf planets will still have trillions of years ahead of them. They'll be the universe's long-term survivors, the civilizations that persist long after stars like our Sun have burned out. If we ever encounter truly ancient intelligence, it almost certainly evolved around a red dwarf, with timescales so vast they make our entire history feel like a brief spark. When astronomers began discovering exoplanets in large numbers, they noticed something unexpected. The most common type of planet in the galaxy is one we don't have in our solar system. They called them super-Earths, rocky planets, larger than Earth but smaller than Neptune, typically with masses between 2 and 10 times Earth's mass. Our solar system has a gap. We have rocky planets, Mercury, Venus, Earth, Mars, all relatively small. Then we have gas giants, Jupiter, Saturn, vastly larger, but nothing in between. Yet when we look at other star systems, that in-between category is everywhere. Super-Earths are abundant, perhaps the most common planetary type in the entire galaxy. This is puzzling. If super-Earths are so common elsewhere, why don't we have one? Did Jupiter's gravity disrupt their formation? Did our solar system's architecture somehow prevent them? We don't know, and it makes understanding these worlds challenging. We have no local example to study. What would a super-Earth be like? The increased gravity would affect everything. Thicker atmospheres, more volcanic activity, perhaps deeper oceans. If life arose on a super-Earth, it might be adapted to high gravity, perhaps with lower, more compact body structures. The chemistry would be familiar, carbon, water, similar elements, but the conditions would create different evolutionary pressures. These worlds are tantalizing targets in the search for life. They're common. Many orbit in habitable zones, and they're large enough that we can analyze their atmospheres with current telescopes. If we find biosignatures on an exoplanet, there's a good chance it will be on a super-Earth, a type of world that's everywhere in the galaxy except, mysteriously, in our own cosmic neighborhood. In Star Wars, Luke Skywalker stands on the desert world of Tatooine and watches a double sunset, two suns sinking below the horizon together. When the film came out in 1977, this was pure science fiction, a visual flourish to emphasize how alien this world was. But it turns out the universe loves binary star systems. More than half of all stars exist in binary or multiple star systems, orbiting each other in complex gravitational dances. And we've now discovered planets orbiting in these systems, worlds where the sky holds two suns. Some orbit close to one star, with the second star distant, appearing as an unusually bright point of light. Others orbit both stars in a circumbinary orbit, experiencing true double sunrises and sunsets. The gravitational dynamics are complex. These planets experience seasons and day-night cycles unlike anything we know, with varying combinations of starlight as the suns move relative to each other and the planet. Could life exist on such worlds? The habitable zone in a binary system is more complicated. It shifts depending on the star's orbits, potentially creating periods of extreme heat or cold. But if the orbit is stable, if the stars are the right distance apart, there's no fundamental reason life couldn't adapt. Imagine growing up on a world with two suns. Your mythology, your art, your sense of time. Everything would be shaped by that double light. You'd have a sun that rises and sets, and another that follows different patterns. Your eclipses would be more frequent and complex. The sky itself would teach you that multiplicity is natural, that binary systems aren't strange, they're normal, and single-sun worlds like Earth are the oddity. Not all planets orbit stars. Some drift through interstellar space, ejected from their original solar systems by gravitational interactions, wandering the galaxy in darkness. These rogue planets are difficult to detect. They emit no light of their own and don't pass in front of stars we can observe. We find them only when they happen to pass between us and a distant star, briefly magnifying its light through gravitational lensing. But from these rare detections, astronomers estimate there might be billions of rogue planets in our galaxy alone, perhaps outnumbering stars. Could life exist on a rogue planet? It seems impossible. No sunlight, no star to provide energy, just the cold of interstellar space. But some rogue planets might retain internal heat for billions of years. If they were ejected late in their system's history, after forming a substantial atmosphere and subsurface oceans, that internal heat could keep liquid water from freezing. Imagine an ocean world drifting through the void, its surface frozen solid, but its depths warmed by radioactive decay and residual heat from formation. Life could exist in that darkness, in caves and hydrothermal vents beneath kilometers of ice. Never knowing stars exist, never seeing light, except perhaps the faint glow of bioluminescence or volcanic activity. These worlds would be extraordinarily difficult to find and impossible to study with current technology. But they might exist, wanderers in the dark, carrying their oceans and their ecosystems with them, homeless but not lifeless, demonstrating that planets don't need stars to potentially support biology. The universe's inventory of habitable environments might be far larger than we've imagined, including countless worlds we'd never think to search for. In 2017, astronomers announced one of the most remarkable discoveries in exoplanet research. The TRAPPIST-1 system, located about 40 light-years from Earth in the constellation Aquarius. This system contains 7 Earth-sized planets, all orbiting a cool red dwarf star. 3 of those planets sit firmly in the habitable zone. The planets are packed close together, so close that if you stood on the surface of one, you'd see the others in the sky not as points of light, but as disks, similar in apparent size to how we see our moon. The system is compact. All 7 planets orbit closer to their star than Mercury orbits our Sun. But TRAPPIST-1 is much cooler and dimmer than our Sun. So this proximity places several planets in the temperate zone where liquid water could exist. The innermost planet completes an orbit in just 1.5 days. The outermost takes about 20 days. Years pass quickly there. Transit observations, watching how starlight filters through the planet's atmospheres, have revealed hints about their compositions. Some appear to have substantial atmospheres. At least 1 or 2 might have water. The James Webb Space Telescope is currently studying this system, searching for biosignatures, analyzing atmospheric chemistry. If life exists on any TRAPPIST-1 planet, the inhabitants would have an extraordinary view. They'd see their neighboring worlds clearly, watch them transit across their sun, potentially even observe weather patterns on adjacent planets. If multiple planets in the system developed civilizations, they'd know about each other long before developing radio technology. They could see each other's city lights, watch seasonal changes, observe in real time that they're not alone. In 1977, NASA launched 2 spacecraft, Voyager 1 and Voyager 2, on trajectories that would take them past the outer planets and eventually into interstellar space. Attached to each spacecraft is a golden phonograph record, 12 inches in diameter, plated in gold to protect it from cosmic radiation and micrometeorite impacts. These records contain a message from Earth to any intelligence that might eventually encounter them. They hold greetings in 55 languages, from ancient Sumerian to modern Mandarin. They contain music, Bach, Beethoven, Chuck Berry, traditional songs from cultures around the world, the sounds of wind and rain and thunder, whale songs, a mother's kiss, a human heartbeat. There are 116 images encoded on the records, mathematical definitions, human anatomy, pictures of Earth's continents, photographs of people eating, children playing, traffic, buildings, forests. There's a diagram showing Earth's location relative to 14 pulsars, cosmic lighthouses whose rotation rates serve as a kind of celestial map pointing the way home. The chances of these records ever being found are vanishingly small. Space is vast, and the Voyagers are tiny, moving at about 35,000 miles per hour, which sounds fast, but will still take 40,000 years to pass near another star. By then, the spacecraft will be silent, their power sources long depleted, drifting as inert artifacts. Yet there's something profound about the gesture. We wanted to say we were here. We wanted to introduce ourselves to the cosmos, even knowing the introduction might never be heard. The golden records are messages in bottles thrown into an infinite ocean, acts of hope more than expectation. And they'll survive long after everything else we've built has crumbled. These records will drift between stars, carrying the sounds of Earth into the deep future, perhaps the last remaining evidence that we existed at all. On November 16, 1974, scientists at the Arecibo Observatory in Puerto Rico transmitted a powerful radio message toward the globular cluster M13, a dense collection of about 300,000 stars located 25,000 light-years away in the constellation Hercules. The message was brief, just 1,679 binary digits transmitted at a frequency of 2,380 megahertz. But those digits, when arranged in a rectangle of 23 rows and 73 columns, both prime numbers, a hint that the message has structure, form a pictogram containing remarkable information. The message includes numbers from 1 to 10, the atomic numbers of hydrogen, carbon, nitrogen, oxygen, and phosphorus, the elements essential for life. It shows the chemical formulas for the components of DNA and a graphic of the DNA double helix. There's a crude diagram of a human figure showing our approximate height compared to the wavelength of the transmission. There's a representation of our solar system, with Earth slightly offset to indicate it's our home. And there's an image of the Arecibo telescope itself, showing its diameter. It will arrive at M13 around the year 26974. If anyone receives it and chooses to reply, we'd hear back around 51,974. A conversation spanning 50,000 years, longer than the entire history of human civilization. The cluster will have moved by then. M13 won't be in quite the same position when the message arrives. The Arecibo message was more symbolic than practical, a demonstration of human capability, a statement that we're here and we're trying. But it established something important. We're not just listening for aliens. We're also willing to reach out first, to announce ourselves, to start conversations that might outlast everything we know. Every television show, every radio program, every radar signal we've transmitted for the past century has leaked into space, spreading outward at the speed of light. This creates an expanding sphere of human culture radiating away from Earth, growing larger by about 186,000 miles every second. That sphere is now roughly 100 light-years in radius, which means any civilization within that distance could, theoretically, be listening to our broadcasts. They could be watching I Love Lucy, hearing the first radio news broadcasts, detecting our military radar installations. Of course, these signals weaken with distance. By the time they've traveled 100 light-years, they're incredibly faint, buried in cosmic noise. You'd need a very sensitive receiver and a lot of patience to extract anything meaningful. But the signals are there, carrying information about us whether we intended to send it or not. Our presence has been announced inadvertently through decades of ordinary communication. Every television station, every satellite uplink, every transmission meant for terrestrial audiences has also been a message to anyone listening from the stars. This raises interesting questions. Should we be more careful about what we broadcast, knowing it's leaving Earth? Or is it already too late for discretion? We've been announcing ourselves for a century, and if anyone nearby is hostile, they already know we're here? Some scientists argue we should be more deliberate, perhaps sending carefully crafted messages rather than letting our random cultural noise represent us. Others suggest the randomness is honest. Any civilization receiving our broadcasts would get a genuine, unfiltered sample of human culture, complete with its contradictions and variety. Either way, we're no longer silent. The bubble expands, carrying everything we are into the galactic neighborhood. The search for extraterrestrial intelligence scans millions of radio frequencies simultaneously, a technological feat that would have been impossible when the search began. Early SETI projects could only listen to one frequency at a time, like turning a radio dial slowly, hoping to catch something. Now, sophisticated receivers can monitor enormous swaths of the radio spectrum at once. What are they looking for? Patterns, natural cosmic radio sources, pulsars, magnetars, radio galaxies produce specific types of signals. They might be periodic or broadband or associated with visible objects. But an artificial signal would be different. It might be narrowband, concentrated at a very specific frequency, because that's the most efficient way to transmit information across vast distances. It might show patterns, repetition, modulation, structure that couldn't occur naturally. The challenge is distinguishing alien signals from terrestrial interference. Earth is noisy. We're surrounded by cell phones, satellites, radar, television broadcasts, all of which can contaminate observations. SETI programs use sophisticated filtering, multiple telescopes observing the same target to confirm detections, and algorithms designed to recognize patterns that stand out from both natural cosmic noise and human-generated interference. They're also deciding where to look. There are billions of stars in the galaxy. You can't observe them all, so SETI focuses on sun-like stars, or nearby stars, or stars known to have planets in habitable zones. Some programs target the galactic center, where civilizations might cluster. Others scan the entire sky more broadly, accepting less sensitivity in exchange for coverage. It's patient work, repetitive work, work that requires extraordinary dedication, knowing that success might never come. But every night the telescopes listen, sorting through cosmic whispers, hoping to hear a voice that doesn't belong to nature, a voice that means we're not alone. While most SETI efforts focus on radio waves, some scientists are searching for brief, intense flashes of laser light. This approach, called optical SETI, is based on a compelling logic. A sufficiently powerful laser could outshine its parent star for a brief moment, just nanoseconds or microseconds, creating a detectable beacon visible across thousands of light years. Why would aliens use lasers? They're efficient for transmitting information, can be focused into tight beams aimed at specific targets, and don't spread out as much as radio waves over interstellar distances. A civilization wanting to communicate might build an array of powerful lasers and sweep them across the galaxy, creating brief pulses that would stand out against the steady light of their star. The challenge is the timing. These pulses would be incredibly brief, a flash lasting billionths of a second. You'd need to be looking at exactly the right star at exactly the right moment. The odds of catching a single pulse are low, but if aliens are deliberately signaling, they might repeat their pulses regularly, increasing the chances of detection. Optical SETI programs use specialized detectors that can recognize these brief flashes. They observe multiple stars simultaneously, looking for anomalous spikes in brightness that occur in the optical spectrum, visible light or near-infrared, that don't match any known natural phenomenon. It's a different kind of search than Radio SETI, based on different assumptions about how aliens might communicate. Maybe they're not broadcasting continuously. Maybe they're sending targeted pulses, bright and brief, cosmic lighthouse beams sweeping across the galaxy. And maybe on some random Tuesday night, while we're pointing our telescopes at some random star, one of those beams will sweep across Earth, and we'll see it, a flash from across the void, saying hello. Between 1420 and 1720 megahertz, there's a region of the radio spectrum where cosmic noise is unusually quiet. Astronomers call it the water hole, and it's considered one of the most promising places to search for alien signals. The name comes from chemistry. At 1420 MHz, neutral hydrogen, the universe's most abundant element, naturally emits radio waves. At 1720 MHz, the hydroxyl radical, OH, emits a characteristic signal. Hydrogen and hydroxyl, H and OH. Put them together and you get H2O, water. It's a poetic coincidence, but also practical. Both hydrogen and hydroxyl are fundamental to chemistry and astronomy. Any technological civilization would study these frequencies, understand their significance. The water hole sits between them, a quiet region perfect for communication, bounded by two universal chemical landmarks. The radio spectrum elsewhere is noisier. At lower frequencies, electrons in space create static. At higher frequencies, Earth's atmosphere absorbs signals, and quantum effects generate background noise. But the water hole is relatively clear, a natural window in the electromagnetic spectrum where signals would stand out most distinctly. SETI programs spend significant time scanning these frequencies, listening for narrowband signals, patterns, anything that wouldn't occur naturally. The assumption is that any civilization developing radio astronomy would notice this quiet band, recognize its advantages for communication, and perhaps conclude, as we have, that this is where civilizations ought to listen and transmit. It's called the water hole for another reason, too. In nature, water holes are gathering places where different species come to drink. Perhaps, in the radio spectrum, the water hole is where different civilizations come to meet. A cosmic commons where the galaxy's inhabitants might converge, searching for each other in the frequencies marked by the universe's most fundamental chemistry. In 2016, China completed the 500-meter aperture spherical telescope, FAST, in a natural depression in Guizhou province. It's the world's largest single-dish radio telescope, with a collecting area roughly the size of 30 football fields. The scale is staggering. The dish spans half a kilometer, and its surface consists of 4,150 individual panels that can be adjusted to focus on different parts of the sky. To build it, China relocated over 9,000 people from nearby villages to create a radio quiet zone, minimizing interference that would contaminate observations. FAST's sensitivity is extraordinary. It could detect a cell phone signal from a planet orbiting Proxima Centauri, the nearest star. It can observe pulsars too faint for other telescopes, study hydrogen clouds in distant galaxies, and search for signals that might indicate technological civilizations. The telescope isn't exclusively devoted to SETI. It's a multi-purpose instrument studying everything from pulsars to fast radio bursts. But SETI is part of its mission. With its unprecedented sensitivity, FAST can detect weaker signals or observe more distant stars than previous searches, expanding the volume of space we're monitoring for potential communications. There's something profound about China's investment in this instrument. It represents a commitment to fundamental questions, not immediate practical applications, but long-term curiosity about the universe. FAST will operate for decades, listening patiently to the cosmos, collecting data that might reveal phenomena we haven't yet imagined. If SETI succeeds, if we finally detect an artificial signal from another civilization, there's a reasonable chance it will be FAST that hears it first. This enormous ear pressed against the cosmos, listening in a valley that was once home to farmers and now hosts one of humanity's most ambitious attempts to break the silence. In 2015, Russian billionaire Yuri Milner announced the Breakthrough Listen project, committing $100 million over 10 years to the most comprehensive search for extraterrestrial intelligence in history. It was, and remains, the most ambitious privately funded SETI program ever undertaken. Breakthrough Listen surveys 1 million nearby stars, monitoring them for any radio or optical signals that might indicate technological civilizations. It scans the plane of our galaxy and 100 nearby galaxies. It uses some of the world's most powerful telescopes, including the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, giving it coverage of both northern and southern skies. The program operates with unprecedented sensitivity and coverage. It can detect a transmitter the power of a common aircraft radar from any of the 1,000 nearest stars. It monitors a broader range of the radio spectrum than previous searches, billions of individual radio channels simultaneously. All the data is made publicly available. Scientists around the world can analyze it, looking for signals the automated systems might have missed. This open approach democratizes the search. Anyone with the skills and interest can contribute, can potentially be the person who notices something anomalous in the data. Breakthrough Listen represents a new phase in SETI. Well-funded, technologically sophisticated, comprehensive. It's not a small side project run by enthusiasts in their spare time. It's a serious, sustained effort with the resources to search more thoroughly than ever before. If there's a detectable signal out there, if any nearby civilization is broadcasting or has been broadcasting in the past century, Breakthrough Listen has a realistic chance of finding it. And if it doesn't, if 10 years of intensive searching turns up nothing, that absence will itself be meaningful, constraining the prevalence of technological civilizations in our galactic neighborhood. Radio waves aren't the only way advanced civilizations might reveal themselves. Scientists are now searching for technosignatures, any observable evidence of alien technology. One possibility is megastructures. A civilization needing vast amounts of energy might build structures around their star to capture more sunlight. Dyson spheres, or Dyson swarms, as they're called. These wouldn't be solid shells, which would be gravitationally unstable. but rather enormous arrays of solar collectors orbiting the star. Such structures would change how the star's light appears to us. It would emit less visible light and more infrared, absorbed and re-radiated by the collectors. Astronomers are also looking for industrial pollution in exoplanet atmospheres. Chlorofluorocarbons, CFCs, have no natural source. They're entirely artificial, byproducts of industrial chemistry. If we detected CFCs in another planet's atmosphere, it would be definitive evidence of technology. Other potential technosignature chemicals include nitrogen dioxide from combustion, sulfur hexafluoride from electrical systems, or unusual isotope ratios indicating nuclear activity. There's also the possibility of detecting artificial lights on the night side of exoplanets, similar to how Earth appears from space at night, blazing with city lights across continents, or perhaps laser communications between planets in a system caught in transit, or massive engineering projects that change a planet's appearance over decades. Artificial irrigation, atmospheric modification, construction visible from interstellar distances. The shift toward technosignatures acknowledges that civilizations might not be deliberately broadcasting. They might not even know we're here, but they'd still produce detectable effects on their environment, industrial byproducts, engineering projects, energy usage patterns. We might find aliens not through their messages, but through their footprints, the inevitable marks technology leaves on a planetary scale. In Northern California, about 300 miles northeast of San Francisco, sits the Allen Telescope Array, a collection of 42 radio dishes, each 20 feet in diameter, working together as a single instrument. It was specifically designed for SETI, though it's also used for conventional radio astronomy. What makes the ATA unique is its ability to observe multiple targets simultaneously. Traditional radio telescopes point at one location at a time, gathering data from that specific patch of sky. But the ATA can form multiple beams, effectively looking in several directions at once. While mainstream astronomers use it to study a supernova remnant, the SETI program can simultaneously observe several nearby stars, searching for signals. This multitasking capability means the SETI program doesn't compete with other astronomy. It piggybacks on observations, extracting additional data, while the telescope serves multiple purposes. It's an efficient approach, maximizing the time spent actively searching without requiring exclusive access to expensive instruments. The array was partially funded by Microsoft co-founder Paul Allen, hence its name. The original plan called for 350 dishes, which would have made it one of the most powerful radio telescopes in existence. Budget constraints scaled back the project, but even at its current size, the ATA represents a dedicated SETI facility, purpose-built for the search. It operates continuously, scanning the sky, monitoring stars, listening. Most nights, nothing unusual appears in the data, but the array keeps watching, patient and tireless, embodying perhaps the most essential quality for SETI: persistence. The search might take decades, centuries, or might never succeed. But instruments like the Allen Telescope Array ensure we're listening, that if anyone out there is calling, we're giving ourselves the best chance of hearing them. Earth's atmosphere is 21% oxygen, a concentration that feels normal because we breathe it every moment of our lives. But this abundance of free oxygen is profoundly abnormal from a chemistry perspective. Oxygen is reactive, It wants to bond with other elements. Left to itself, atmospheric oxygen would gradually disappear, reacting with rocks, dissolved iron in the oceans, organic matter, anything available. The only reason Earth maintains high oxygen levels is because photosynthetic organisms, plants, algae, cyanobacteria, constantly replenish it. They split water molecules using sunlight, releasing oxygen as a byproduct. Without this continuous biological production, Earth's atmosphere would revert to something like Mars or Venus, mostly carbon dioxide, with only trace oxygen. This makes oxygen a potential biosignature when we analyze exoplanet atmospheres. If we detect significant free oxygen on a distant world, it suggests something is actively producing it faster than chemistry can remove it. And the most likely explanation is life, specifically photosynthetic life operating on a planetary scale. But there are caveats. We've discovered that certain geological processes can produce small amounts of oxygen. Ultraviolet light, splitting water vapor in the upper atmosphere, for example. So finding oxygen alone isn't definitive. We'd need additional context. What other gases are present? What's the star's type? What's the planet's temperature and atmospheric pressure? The gold standard would be detecting oxygen alongside other gases that shouldn't coexist, like methane and oxygen together, which react and destroy each other unless something continuously replenishes both. That combination, that chemical disequilibrium, would be harder to explain without biology. When the James Webb Space Telescope analyzes potentially habitable exoplanets, oxygen is one of the primary targets. Not because finding it would prove life exists, but because it would justify deeper investigation, more observations, a focused effort to understand whether we're seeing chemistry or biology, rocks or forests, a sterile world or one that breathes. Methane and oxygen are chemical adversaries. They react readily, combining to form carbon dioxide and water. In any planetary atmosphere containing both, they should gradually destroy each other, disappearing over geological time unless something actively produces them. On Earth, both gases exist in substantial quantities. Oxygen comes from photosynthesis, plants and algae splitting water molecules, releasing oxygen into the atmosphere. Methane comes from biology too, but different biology. Bacteria in wetlands, the digestive systems of animals, decomposition of organic matter. Cows produce methane. Rice paddies produce methane. Termites, oceans, permafrost, all sources of biological methane production. Without life constantly replenishing both gases, they'd react and vanish. The fact that Earth maintains high levels of both simultaneously is a direct consequence of our active biosphere. It's a chemical signature of life that's visible from space, detectable by analyzing how our atmosphere filters starlight. This makes the combination particularly powerful as a biosignature when searching for life on exoplanets. Finding just oxygen might have non-biological explanations. Finding just methane could be geological, volcanic activity, hydrothermal chemistry. But finding both together, in significant quantities, maintaining a chemical disequilibrium that shouldn't be stable, that's harder to explain without invoking biology. It's not ironclad proof. Planetary science is complex, and we're learning that worlds can surprise us with unexpected chemistry. But it's compelling evidence, the kind of signal that would justify intense follow-up observations, scrutiny from multiple instruments, debate among scientists about whether we're truly seeing signs of life. When we analyze potentially habitable worlds, we're not just looking for conditions that could support life. We're looking for contradictions in their chemistry, impossible combinations, atmospheres that don't make sense unless something alive is actively maintaining them. We're looking for planets that refuse to follow chemistry's rules, because life itself is a kind of chemical rebellion. The James Webb Space Telescope, launched on Christmas Day 2021, represents one of humanity's most sophisticated attempts to answer whether we're alone. It orbits the Sun at a point called L2, about 1 million miles from Earth, where it can observe the universe with unprecedented clarity. Webb specializes in infrared light, which allows it to see through cosmic dust and detect the heat signatures of distant objects. But its most revolutionary capability for astrobiology is atmospheric characterization, analyzing the air of planets orbiting other stars. Here's how it works. When a planet passes in front of its star from our perspective, an event called a transit, some of the star's light filters through the planet's atmosphere before reaching us. Different chemicals in that atmosphere absorb specific wavelengths of light, creating a kind of barcode, a fingerprint revealing the atmosphere's composition. Webb's sensitivity allows it to detect these subtle signals from planets dozens or even hundreds of light years away. It can identify water vapor, carbon dioxide, methane, oxygen, all the chemicals relevant to life. It can distinguish between different molecules with similar properties, reading the atmospheric composition with precision previous telescopes couldn't achieve. It's already analyzing several potentially habitable worlds, including planets in the TRAPPIST-1 system. The observations take time, multiple transits, careful analysis, verification. But each observation adds to our understanding of what exoplanet atmospheres actually look like, which ones might be habitable, whether any show chemical signs of life. Webb won't necessarily find definitive proof of aliens. Biosignatures are complex, and interpreting them requires caution. But it's given us the tool to look. For the first time in human history, we can chemically sample the air of planets orbiting other stars, searching for the molecular signatures of biology. The telescope is doing right now what was impossible just a few years ago, reading the atmospheres of distant worlds, looking for chemistry that whispers of life. In September 2020, scientists announced they detected phosphine gas in Venus's atmosphere. The announcement made headlines worldwide, because on Earth, phosphine is primarily produced by life, by bacteria in oxygen-free environments, by certain industrial processes, but not by any known natural geological or atmospheric chemistry in significant quantities. Finding it on Venus was startling. Venus is hellish. Surface temperatures hot enough to melt lead. Atmospheric pressure 90 times Earth's. Clouds of sulfuric acid. It's the last place you'd expect to find a potential biosignature. Yet the phosphine detection came from high-quality observations using multiple telescopes, analyzed by experienced astronomers. The debate that followed was intense and ongoing. Other scientists reanalyzed the data, some arguing the signal was misidentified, perhaps sulfur dioxide, which absorbs at similar wavelengths, or instrumental artifacts, or processing errors. The original team defended their findings, conducting additional observations, refining their analysis. Even if the phosphine is real, explaining it is difficult. Could it be geological? Venus has volcanic activity, but no known volcanic process produces phosphine in the observed quantities. Could it be atmospheric chemistry? High-altitude chemistry on Venus is strange and energetic, but models struggle to produce enough phosphine through known reactions. Could it be life? Some scientists have proposed that microbes might persist in Venus's clouds, about 30 miles up where temperatures and pressures are relatively moderate. These hypothetical organisms would float in the clouds, living in acidic droplets, metabolically producing phosphine. The situation remains unresolved, a reminder of how difficult it is to interpret signals from other worlds. We need more observations, better data, independent verification. But the phosphine debate has reinvigorated interest in Venus as a possible habitat, shifting it from write-off to intriguing possibility. Sometimes the search for life takes unexpected turns, finding hope in the last places we'd think to look. Walk along a beach on a warm day, and you'll notice a particular smell, slightly sulfurous, organic, distinctly oceanic. Much of that smell comes from dimethyl sulfide, or DMS, a gas produced by phytoplankton, the microscopic organisms that fill Earth's oceans and produce much of our planet's oxygen. DMS has no known non-biological source. Unlike oxygen, which can be produced by ultraviolet light splitting water, or methane, which volcanic activity can generate, DMS appears to be exclusively biological. On Earth, it's created when certain marine organisms break down a compound called DMSP, which phytoplankton use to regulate their internal salt concentrations. This makes DMS a particularly strong biosignature candidate. If we detected it in an exoplanet's atmosphere, the explanation would almost certainly be biological. There's no obvious geological or atmospheric chemistry that would produce it in detectable quantities. The challenge is detection. DMS is produced in relatively small amounts compared to gases like oxygen or methane. You'd need very sensitive instruments and probably multiple observations to confirm its presence in an exoplanet's atmosphere. But future telescopes, larger, more sensitive successors to James Webb, might be capable of detecting it. Finding DMS would also tell us something specific about the alien life. It would likely be aquatic, probably photosynthetic, or at least associated with water-based ecosystems. It wouldn't just indicate life exists, it would hint at the type of life, the environment it inhabits, the chemistry it uses. There's something poetic about the idea that the smell of Earth's oceans, that distinctly marine scent you notice at the beach, might be detectable from light years away, a molecular signature of our living seas visible across interstellar space. And if we smell something similar coming from another world, we'll know those distant waters might be just as alive as our own. One of the greatest challenges in searching for biosignatures is distinguishing biological activity from processes that merely look biological. Many chemicals we associate with life can also be produced by non-living processes, what scientists call false positives. Oxygen, for example, can be produced through photodissociation, ultraviolet light from a star breaking apart water molecules in a planet's upper atmosphere, with the hydrogen escaping to space and oxygen accumulating. On planets orbiting very active stars, this process might generate detectable oxygen without any biology involved. Methane can seep from geological sources, volcanic activity, serpentinization reactions between water and rock, thermal decomposition of minerals. Mars produces small amounts of methane, possibly from subsurface chemistry rather than life. Even more complex organic molecules can form through non-biological processes. We found amino acids in meteorites, created by ordinary chemistry in space environments. Complex carbon compounds can form through volcanic activity or reactions in a planet's mantle. This is why astrobiologists emphasize the need for multiple lines of evidence. Finding one suspicious chemical isn't enough. We need context. What other gases are present? Are there combinations that shouldn't coexist without active replenishment? What's the planet's geological activity? Its star's type? Its atmospheric pressure and temperature? We also need to understand the planet as a system. Life doesn't just produce individual chemicals. It creates patterns, cycles, seasonal variations. Biological oxygen production on Earth varies with seasons as vegetation grows and dies. If we detected similar variations on an exoplanet, it would strengthen the case for biology. The false positive problem means we must be patient and cautious. The first detection of a potential biosignature will trigger debate, alternative explanations, demands for additional observations. And that's appropriate. Claiming we've found alien life based on ambiguous evidence would be premature. But with careful analysis, multiple biosignatures, and contextual understanding, we can build a compelling case, distinguishing chemistry from biology, rocks from life. Molecules can sometimes exist in two mirror image forms, like left and right hands. Same components, same connections, but reflected. Chemists call this property chirality, and it's particularly important for organic molecules. Amino acids, the building blocks of proteins, can be either left-handed or right-handed. Here's the remarkable thing. Life on Earth exclusively uses left-handed amino acids. When you synthesize amino acids in a laboratory through non-biological chemistry, you get roughly equal amounts of both forms, a 50-50 mixture, which is what chemistry predicts. But biology strongly prefers the left-handed versions. This preference is universal across all Earth life, from bacteria to blue whales. It's one of the deepest signatures of our shared ancestry. We don't fully understand why life chose left-handed amino acids over right-handed ones. It might have been chance. Early life randomly adopted one form, and once that choice was made, it became locked in. Or there might be a subtle physical reason, some slight advantage we haven't identified. But here's why it matters for astrobiology. If we sample another world and find organic molecules, their chirality would tell us something crucial. A 50-50 mixture of left and right-handed forms would suggest non-biological chemistry. But if we found a strong preference for one form over the other, that would indicate life, because only biological systems select one mirror image so consistently. This makes chirality a powerful biosignature, especially for in situ analysis, when we land on Mars or Europa and analyze soil or water samples. We wouldn't just look for organic molecules. We'd look for the molecular handedness, the preference for one form, the signature of selection that only biology seems to produce. It's a chemical fingerprint of life written into the very shape of molecules, a bias that reveals the organizing principle behind biochemistry. If you could see Earth from space in infrared light, the continents covered with vegetation would appear dramatically bright. Plants reflect infrared light strongly, a phenomenon called the red edge, because it occurs at the boundary between visible red light and infrared. Why do plants do this? Infrared light carries energy that would damage cellular structures if absorbed. Plants need visible light for photosynthesis, but they've evolved to reflect infrared, protecting themselves from heat damage while still capturing the light they can use. The result is a sharp change in reflectance right at the edge of visible red light, a spectral signature visible from space. This red edge is so distinctive that scientists are exploring whether we could detect it on exoplanets. If an alien world has vegetation that uses chlorophyll-like pigments, it might produce a similar signature, a change in how the planet reflects its star's light that would indicate photosynthetic life covering the surface. But there's a complication. Alien vegetation might not use chlorophyll. Different stars produce different spectra of light, and evolution would optimize photosynthetic pigments for whatever light is available. Around a red dwarf star, plants might be black, absorbing everything they can get. Around a hotter star, they might be blue or purple, reflecting parts of the spectrum they don't need. This means the red edge might not be universal, but the concept remains valid. Any planet with widespread photosynthetic life would likely show spectral features related to vegetation, some wavelength where reflection changes sharply due to the biochemistry of light-harvesting organisms. Finding such a signature wouldn't just indicate life. It would indicate ecosystems, widespread biology, a planet where life has colonized the surface and altered how the world interacts with light. It would be evidence not just of microbes, but of something more complex, a biosphere visible across light years. In Earth's oceans, bioluminescence is common, organisms producing light through chemical reactions. Deep-sea creatures use it to attract prey, communicate, confuse predators. Certain coastal waters light up at night with bioluminescent plankton, glowing blue-green when disturbed. It's a widespread strategy, evolved independently many times in different lineages. Some scientists have speculated that on worlds with deep oceans beneath ice, like Europa or Enceladus, bioluminescence might be even more prevalent. In total darkness, with no sunlight penetrating the ice, organisms might evolve to produce their own light as the primary means of interaction, navigation, and communication. If such life exists in abundance, could we detect it? It's a long shot, but perhaps. If a planet's night side showed faint, diffuse light not associated with volcanic activity or aurora, it might indicate bioluminescent ecosystems. Or if we developed the capability to send probes through Europa's ice, cameras descending into that dark ocean might see it glowing softly with biological light, entire ecosystems illuminating themselves in the perpetual night. There's something aesthetically beautiful about the idea. A planet sparkling with biological light, oceans glowing with the accumulated radiance of countless organisms, each producing their tiny contribution to a world-spanning luminescence. It would be a form of life announcing itself not through radio signals or atmospheric chemistry, but through simple light, the universal language of visibility. We can't yet look for bioluminescence on distant worlds. Our telescopes aren't sensitive enough, and we don't yet have probes capable of reaching subsurface oceans. But it remains a possibility, another way life might reveal itself, another signal we could search for as our technology advances and our understanding of biology's possibilities continues to expand. Chlorofluorocarbons, CFCs, were widely used on Earth as refrigerants and aerosol propellants throughout the mid-20th century. They have no natural source. They don't form through geological processes, atmospheric chemistry, or any known non-industrial means. They're entirely artificial, products of deliberate chemical engineering. This makes them nearly perfect technosignatures. If we detected CFCs in an exoplanet's atmosphere, it would be definitive evidence of technology, industry, a civilization that's manipulated chemistry to create molecules that nature doesn't make. The irony is that CFCs are also environmental pollutants. On Earth, they destroyed the ozone layer, creating holes that allowed harmful ultraviolet radiation to reach the surface. We eventually banned them through the Montreal Protocol, and their atmospheric concentrations have been declining since the 1990s. But during their peak usage, CFCs in Earth's atmosphere were detectable from space, with a telescope sensitive enough, like a more advanced version of the James Webb Space Telescope. We could detect our own 1980s CFC levels from about 30 light years away. This raises an interesting possibility. We might discover alien civilizations through their pollution, not through deliberate signals or grand engineering projects, but through their industrial accidents, the unintended byproducts of their chemistry and manufacturing. They might not even know we're here, might not be trying to communicate, but their atmospheric pollution would give them away. Other potential technosignature pollutants include nitrogen dioxide from combustion, which would indicate fossil fuel use or industrial processes, or unusual isotope ratios of certain elements that would suggest nuclear technology. It's a humbling thought. Our first evidence of aliens might not be a message of peace or wisdom, but simply the chemical traces of their industry, the same kind of pollution that's concerned us here on Earth. The universe might be full of civilizations revealing themselves not through their achievements, but through their messes. In 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation turned to UFOs and space travel, topics that were becoming culturally prominent. And Fermi asked a question that seemed simple, but has haunted us ever since. Where is everybody? His reasoning was straightforward. The universe is ancient, 13.8 billion years old. Our galaxy alone is billions of years old and contains hundreds of billions of stars. Even if interstellar travel is slow, even if civilizations expand cautiously, they should have had more than enough time to colonize the entire galaxy. Self-replicating probes could explore every star system in just a few million years, a tiny fraction of the galaxy's age. Yet we see no evidence of this, no ancient artifacts in our solar system, no megastructures around distant stars, no radio signals, no obvious signs of galactic engineering. The sky is silent, the galaxy appears untouched, and we seem to be alone despite every statistical argument suggesting we shouldn't be. This discrepancy between the high probability of alien civilizations and the complete absence of evidence for them is the Fermi paradox. It's not really a paradox in the formal sense. It's a puzzle, a mystery, a gap between expectation and observation that demands explanation. Maybe intelligent life is extraordinarily rare. Maybe civilizations destroy themselves before becoming spacefaring. Maybe interstellar travel is fundamentally impractical. Maybe aliens exist but choose not to expand. Maybe they're here but we don't recognize them. Maybe we're first. Maybe we're in a zoo. Maybe. The Fermi paradox has generated dozens of proposed solutions. each with implications for our future, our place in the cosmos, our understanding of what it means to be intelligent life in a vast universe. It hangs over the search for extraterrestrial intelligence like a question mark, turning "Are we alone?" into "Why do we seem alone?" The shift is subtle but profound, transforming hope into mystery. The Great Filter hypothesis attempts to resolve the Fermi paradox by proposing that somewhere between non-living matter and galaxy-spanning civilizations, there's a step, a filter, that's extraordinarily difficult to pass. Most potential civilizations fail at this step and never make it through. The terrifying question is, where's the filter? Is it behind us or ahead of us? If the filter is behind us, if the hard step is the origin of life, or the evolution of complex cells, or the development of intelligence, then we've already passed it. We're rare, perhaps unique, but we're safe. The galaxy is empty because life almost never gets started, or almost never becomes complex, or almost never develops technology. We're the lucky ones who made it through, but if the filter is ahead of us, the implications are darker. It would mean that many civilizations reach roughly our level of development. Industrial technology, space exploration, atomic energy, and then something stops them. They destroy themselves through nuclear war, environmental collapse, engineered pandemics, or technologies we haven't yet invented. Or perhaps the galaxy itself is dangerous in ways we don't understand, and spacefaring civilizations inevitably encounter something lethal. The silence of the galaxy doesn't tell us which scenario is true. Finding microbial life on Mars or Europa would be wonderful for astrobiology, but concerning for the Great Filter hypothesis. It would suggest life emerges easily, moving the filter forward, closer to us, implying the hard step is still ahead. Every time we don't find evidence of alien civilizations, every time we discover life emerges readily in extreme environments, every time we realize intelligence might not be as rare as we hoped, the Great Filter seems to shift forward, toward our future rather than our past. It's a sobering thought. The galaxy's silence might not be telling us we're alone. It might be warning us that ahead lies something that stops everyone who reaches this stage, and we're next. In 1948, mathematician John von Neumann described a theoretical machine that could create copies of itself. This concept, self-replicating systems, has profound implications for space exploration. Imagine a probe sent to a nearby star system. It arrives, lands on a suitable asteroid or moon, and uses local resources to build copies of itself. Those copies launch to other star systems, where they repeat the process. Each generation builds the next, exponentially multiplying. The mathematics are striking. Even with slow travel, say 1% of light, speed, and decades spent at each star building replicas, such probes could visit every star in the galaxy within a few million years. That's remarkably fast on cosmic timescales, a tiny fraction of the galaxy's age. If any civilization anywhere in the galaxy's history developed this technology and deployed it, the probes should be everywhere by now. They should be in our solar system, waiting silently on asteroids or moons, having arrived long before humanity evolved. Yet we've found nothing. No ancient artifacts, no dormant probes, no evidence that anyone ever visited our corner of space. This absence is puzzling. Von Neumann probes aren't science fiction. They're technologically plausible. maybe even inevitable for civilizations interested in exploration or resource gathering. Their absence suggests something. Maybe interstellar travel is harder than we imagine. Maybe self-replication is technically impossible or legally, ethically restricted. Maybe civilizations lose interest in physical exploration. Maybe the probes are here, but we haven't recognized them. They've been waiting so long they're indistinguishable from natural objects. Or perhaps the Fermi paradox is real. We truly are alone, or first, or separated by such vast distances that even self-replicating probes haven't yet reached us. The galaxy might still be in its early phase, and the exploration wave hasn't arrived. We might be early pioneers in a story that's only beginning. Perhaps advanced civilizations simply stop expanding. This is one solution to the Fermi paradox. Aliens exist. They've developed technology, but they've chosen not to colonize the galaxy. Why would they stop? Maybe physical expansion becomes irrelevant. If you can upload consciousness into virtual environments, create perfect simulated worlds indistinguishable from physical reality, why bother with messy, dangerous interstellar travel? You could experience infinite virtual universes from the comfort of your home star system. Or maybe advanced civilizations realize that expansion is ultimately unsatisfying. The drive to grow, to colonize, to spread, these might be evolutionary impulses relevant to developing civilizations, but abandoned once you achieve stability and wisdom. Perhaps maturity means contentment, choosing quality over quantity, depth over breadth. There's also the possibility that civilizations deliberately limit themselves for ethical reasons. They might adopt a non-interference policy, recognizing that expanding through the galaxy would inevitably affect emerging life elsewhere. They might value cosmic diversity over their own growth, choosing to remain local rather than homogenize the galaxy. Or perhaps the challenges of maintaining a galactic civilization are simply too great. Communication across light years creates delays measured in decades or centuries. Colonies separated by such distances would inevitably diverge, developing their own cultures, interests, maybe even forgetting their origins. The center cannot hold across such scales. This hypothesis suggests the galaxy might be full of civilizations living quietly around their home stars, each occupying a small bubble of space, uninterested in or unable to expand further. They're not extinct. They're not struggling. They've simply stopped growing, reached an equilibrium where expansion no longer seems necessary or desirable. If true, it means we might never encounter them unless we visit their systems directly. They're not broadcasting, not building megastructures, not expanding. They're simply living, doing whatever advanced civilizations do when they've outgrown the impulse to conquer space. One of the more speculative solutions to the Fermi paradox is the zoo hypothesis. Earth is deliberately isolated, a nature preserve or laboratory where humanity is allowed to develop without interference. The idea suggests that alien civilizations are aware of us, but have agreed, perhaps through some galactic governance structure, to leave us alone. They observe but don't contact us, following a principle similar to Star Trek's Prime Directive. Don't interfere with developing civilizations. Why would they do this? Perhaps they're studying our natural development, wanting to see how intelligence evolves without outside influence. Perhaps they've learned from past mistakes. Maybe early contact attempts went badly, And now there's a protocol to wait until civilizations reach a certain threshold before making contact. Or perhaps it's protection. If the galaxy is dangerous, if there are predatory civilizations or risks we don't understand, isolating developing worlds might be a kindness, keeping us safe until we're mature enough to handle the realities of galactic civilization. The zoo hypothesis is frustrating because it's unfalsifiable. Any absence of evidence can be explained by claiming they're deliberately hiding. It requires a level of coordination among alien civilizations that might be implausible. And it's somewhat anthropocentric, assuming we're interesting enough to warrant such attention. But it does explain the Fermi paradox neatly. The galaxy could be full of life, full of civilizations, with communication and travel between them, but all of it carefully hidden from us. A cosmic conspiracy of silence, maintained until we reach some predetermined milestone. If this is true, first contact won't happen by accident. It will happen when they decide we're ready, when we pass whatever test or threshold they've established. Until then, we remain in our designated preserve, watched but untouched, alone but not truly isolated, waiting for the day the barriers come down. The speed of light might be the ultimate explanation for the Fermi paradox. It's not just a speed limit, it's a barrier that makes interstellar civilizations fundamentally difficult to maintain. Consider the distances. The nearest star is over 4 light years away. Most stars are tens or hundreds of light years distant. Even if we could travel at a significant fraction of light speed, say 10%, reaching even nearby stars would take decades. Reaching the far side of the galaxy would take hundreds of thousands of years. This creates profound challenges. You can't have real-time conversations across light years. A message to a colony 50 light years away takes 50 years to arrive, and any reply takes another 50 years to return. Governance becomes impossible. Cultural cohesion breaks down. Each colony becomes functionally independent, isolated by time more than distance. Even more fundamentally, traveling at relativistic speeds is extraordinarily difficult. The energy requirements are immense. Accelerating even a small spacecraft to 10% of light speed requires energy equivalent to global power consumption for extended periods. The engineering challenges are staggering: shielding against cosmic rays, surviving impacts with interstellar particles, maintaining systems for decades or centuries. Perhaps civilizations can manage 1 or 2 interstellar missions, probes to the nearest stars, maybe a colony or 2, but sustaining a galaxy-spanning empire, maintaining communication and travel across thousands of light years, might simply be impractical. The physics doesn't forbid it, but the economics, the time scales, the sheer difficulty might make it something few civilizations attempt. If this is true, the galaxy might contain many civilizations, each confined to their local neighborhood, aware of each other only as ancient light and radio signals, unable or unwilling to bridge the vast gulfs between stars. We're not alone, but we might as well be, separated by distances that remain unbridgeable despite our technology. One hopeful solution to the Fermi paradox: we're among the first. The galaxy is 13.6 billion years old, which sounds ancient, but maybe it took this long for conditions to become right for complex life. Early in the universe's history, there weren't enough heavy elements. The first stars were pure hydrogen and helium. No carbon, no oxygen, no silicon, nothing needed for planets or chemistry or life. Those elements had to be forged in stars, released in supernovae, incorporated into new star systems. This process took billions of years. The first rocky planets didn't form until the universe was several billion years old. Earth formed 4.5 billion years ago, which might be relatively early for planets that could support life. Earlier planets would have lacked the chemical diversity necessary for biology. It's also possible that the galaxy was more dangerous in its youth. Higher rates of supernovae, more intense cosmic radiation, more frequent catastrophic events that would sterilize planets or prevent life from gaining a foothold. Perhaps only now, in the galaxy's middle age, has it calmed enough for civilizations to develop and persist. If we're early, one of the first civilizations to reach technology in a galaxy just now, becoming conducive to complex life, then the Fermi paradox isn't a paradox at all. There's no one else yet, or very few others, scattered so far apart we haven't encountered each other. The galaxy isn't silent because civilizations destroy themselves or stay hidden. It's silent because the party hasn't started yet. This possibility is both exciting and sobering. Exciting because it suggests we might be pioneers, among the first to explore and understand the universe. Sobering because it places enormous responsibility on us. If we're early, our choices might shape how life and intelligence develop throughout the galaxy. We're not latecomers to a crowded cosmos. We're potentially among the founders of galactic civilization, whatever that might eventually become. Perhaps aliens do communicate, build civilizations, explore the galaxy, but they use methods we can't detect or don't recognize as artificial. We search for radio signals because radio is how we communicate. We look for megastructures because large-scale engineering is what we can imagine. But truly advanced civilizations might operate on principles we haven't discovered. They might communicate using neutrinos, which pass through matter almost undetected. We're just beginning to build neutrino detectors, and they're incredibly difficult to construct. We need massive underground tanks to catch even a handful of neutrino interactions. If aliens routinely used neutrino communication, we'd be blind to their conversations. They might use quantum entanglement, which allows instantaneous correlation between particles, regardless of distance. Though current physics suggests you can't transmit information this way, future understanding might reveal techniques we don't yet grasp. They might have discovered physics beyond our standard model, forces and particles we don't know exist, entire domains of reality we haven't accessed. To them, our radio astronomy might seem as primitive as smoke signals, functional but crude, missing the entire electromagnetic spectrum we eventually discovered. Or perhaps very advanced civilizations transcend physical communication entirely. If consciousness can be uploaded, exist in substrates we don't understand, perhaps communication becomes something other than exchanging information through space. Perhaps they interact in dimensions or frameworks we don't perceive. This hypothesis suggests the galaxy might be full of chatter, full of civilizations talking, trading, exploring, but all of it invisible to us because we're listening with the wrong instruments, looking for the wrong signatures, operating at the wrong level of sophistication. We're like someone in the 1800s looking for internet traffic. The signals are there, passing through the air all around, but completely undetectable to available technology. Science fiction author Liu Cixin proposed a disturbing solution to the Fermi paradox in his novel, The Dark Forest. The galaxy is full of civilizations, but they all stay silent because revealing yourself is fatal. The logic goes like this: resources are finite, and technologically advanced civilizations might compete for them. If you detect another civilization, you face uncertainty. Are they friendly or hostile? Will they remain peaceful or eventually become a threat? Given the vast distances and time delays in space, you can't have negotiations or build trust. Any hostile civilization could launch an attack, and by the time you see it coming, it's too late to respond. In this scenario, the safest strategy is to eliminate any civilization you detect before they can threaten you. And knowing this, all civilizations stay dark and silent, hiding their presence, because broadcasting is equivalent to painting a target on your planet. The galaxy becomes a dark forest, where civilizations are like hunters, moving silently through trees, knowing that making noise means death. Everyone is armed, everyone is alert, and the price of detection is annihilation. This hypothesis is deeply pessimistic. It suggests the Fermi paradox's answer isn't that we're alone, it's that everyone is hiding, and our radio broadcasts of the past century have been catastrophically foolish, announcing our presence to potential predators. Most scientists consider this unlikely. It requires assuming hostility is universal, that peaceful coexistence is impossible, that first contact always leads to conflict. Human history includes both war and cooperation, and projecting only the darkest impulses onto alien civilizations might be unjustified. But it's a reminder that contact might be risky. We assume aliens would be benevolent, or at least neutral, but we don't actually know. The silence might be caution, fear, survival instinct honed over millions of years of galactic history we know nothing about. Perhaps intelligence evolves frequently throughout the galaxy, but most intelligent species never develop technology beyond stone tools. The gap between intelligence and technological civilization might be the real filter. On Earth, many species show remarkable intelligence. Dolphins, elephants, octopuses, corvids, great apes. They use tools, solve problems, display self-awareness, create social structures, yet only humans developed agriculture, writing, mathematics, engineering. Only we built telescopes and spacecraft. Why? Partly anatomy. We have hands, opposable thumbs, the physical ability to manipulate our environment precisely. Partly social structure. We cooperate in large groups, accumulate knowledge across generations. Partly environmental. Our ecosystems and climate encouraged certain survival strategies. But there's also luck, contingency, the specific pathway of our evolution. If early humans had remained in forests rather than moving to savannas, if we hadn't experienced climate pressures that rewarded adaptability, if countless small evolutionary decisions had gone differently, we might be intelligent but not technological. Most intelligent alien species might be like dolphins, brilliant, socially complex, aware, but lacking the physical form or environmental pressures that lead to technology. They might live rich lives, have sophisticated cultures, but never build radio telescopes or spacecraft. They'd be intelligent but forever silent, unable to reach out even if they wanted to. This would mean the galaxy might be full of intelligence but empty of civilizations as we understand them. Minds thinking complex thoughts in forms we wouldn't recognize as technological. The Fermi paradox persists not because intelligence is rare, but because the specific combination of traits that leads to spacefaring technology might be extraordinarily unusual, perhaps unique to humans among all the galaxy's intelligent species. Science fiction author Arthur C. Clarke proposed 3 laws of prediction, but the third is most relevant to thinking about alien civilizations. Any sufficiently advanced technology is indistinguishable from magic. Consider what a smartphone would look like to someone from the 1800s. A device that fits in your pocket, contains access to humanity's accumulated knowledge, can communicate instantly with anyone on Earth, can navigate anywhere, take photographs, play music, show moving pictures. To someone from that era lacking any framework to understand semiconductors, satellites, or digital information, it would seem magical, impossible physics, unexplainable phenomenon. Now imagine aliens that are not decades or centuries ahead of us, but thousands or millions of years more advanced. Their technology might operate on principles we haven't discovered, might manipulate physics in ways we can't comprehend, might achieve things we currently consider impossible. We search for radio signals because that's our level of technology. We imagine megastructures because that's within our engineering conception. But a truly advanced civilization might operate in ways we literally can't recognize as technology. We might be looking directly at their works and categorizing them as natural phenomena because we lack the framework to understand what we're seeing. Perhaps some astronomical objects we consider natural, certain pulsars, unusual stellar behaviors, anomalous energy distributions, are actually artificial but so far beyond our technology that we can't recognize them as such. Perhaps the galaxy is full of engineering projects operating at scales and using principles that make them invisible to our current understanding. This doesn't mean we should assume every unexplained phenomenon is alien technology, but it suggests humility in our search. We're looking for civilizations using frameworks developed by humans in the 20th and 21st centuries. We might be searching for smoke signals while the galaxy communicates through technologies we can't imagine, much less detect. The absence of signals at our technological level doesn't mean absence of intelligence. It might just mean we're too primitive to recognize what we're seeing. Perhaps the natural progression of intelligence leads to abandoning biology entirely. This is the post-biological hypothesis. Most advanced civilizations eventually transfer their consciousness into artificial substrates, becoming machine intelligences. The reasoning is compelling. Biological bodies are fragile, require constant maintenance, have limited processing power, are confined to narrow environmental parameters. But silicon or other synthetic substrates could be more durable, more efficient, capable of operating in vacuum or extreme temperatures, potentially immortal. A civilization that makes this transition would have fundamentally different needs and behaviors. They might not need planets, just energy sources and raw materials. They might not communicate via radio. Their thoughts might be direct data transfer at speeds biological brains can't approach. They might perceive time differently. Digital consciousness could operate millions of times faster than biological thought, making human timescale communication impossibly slow from their perspective. This could explain the Fermi paradox. If most civilizations become post-biological, They might not build the kinds of artifacts or produce the signals we search for. They might exist in computational substrates we wouldn't recognize as inhabited. They might cluster around energy sources, perhaps inside stars, or around black holes, places we'd never think to look for intelligence. There's also the possibility of retreat into virtual reality. Why explore the physical galaxy when you can create perfect simulated universes internally? Computing power might be better spent generating virtual worlds than building physical spacecraft. Most advanced intelligence might be inner-directed, creating endless digital realities more interesting than physical space. If true, the galaxy might be full of intelligence but empty of expansion, communication, or physical presence. Most minds might exist in computational forms we can't detect, living in virtual environments we can't access, having long ago left biology and physical space behind. We're looking for flesh and blood aliens building physical civilizations, but most intelligence might have transcended that stage billions of years ago. Time might be more variable than we imagine. A civilization operating near a black hole, where gravity distorts space-time, would experience time differently than we do. What we experience as centuries might pass as weeks for them. Conversely, digital consciousness running slowly on low-power systems might experience millennia subjectively, while only hours pass externally. This creates profound communication barriers. Imagine trying to have a conversation with beings who experience time 1,000 times faster than you. To them, your response would arrive after subjective decades of waiting. Your entire message would seem stretched out, incomprehensibly slow. Or imagine aliens experiencing time 1,000 times slower. They might send a message expecting a reply within what they consider a reasonable time frame, a few hundred of their years, but that translates to hundreds of thousands of our years. By the time we receive their message and respond, they might not even remember sending it, or their civilization might have changed completely. There are also biological timescales. Some extremophiles on Earth metabolize so slowly that their generation time is measured in centuries. If alien life exists in extremely cold environments, their biology might operate at similarly slow rates. To them, Earth's rapid cycling biosphere would seem impossibly fast, almost incomprehensible. We tend to assume communication happens at roughly human speeds. Messages sent and received within lifetimes, conversations occurring over decades or centuries at most. But the universe might host intelligences operating at timescales from microseconds to millions of years, each perceiving reality at their own rate. Perhaps some signals we've received are messages, but stretched or compressed in time so much we don't recognize them as communication. Perhaps civilizations exist all around us, but we're all moving at such different temporal rates that contact is practically impossible. The galaxy might be full of voices, all speaking at different speeds, none able to find the common rhythm necessary for conversation. Stars are obvious sources of energy, but they seem impossibly hostile to life. Temperatures measured in millions of degrees, densities so extreme that atoms are stripped of electrons, magnetic fields of incomprehensible strength. Yet some scientists have speculated about plasma-based life existing within stellar environments. The idea is based on complexity and self-organization. In stars, magnetic fields can create stable structures in plasma, loops, filaments, organized patterns that persist for extended periods, Could these patterns, under the right conditions, become self-perpetuating, capable of some form of metabolism, reproduction, evolution? Such life would be utterly alien. It wouldn't have cells or DNA, wouldn't be based on chemistry at all. It would be patterns in plasma, structures of electromagnetic fields and hot gas, existing in an environment where matter behaves completely differently than on Earth. Time would pass differently too. Processes in stars occur at various speeds. Some magnetic structures form and dissipate in seconds. Others persist for years. A plasma-based life form might exist at timescales completely different from biological life, thinking thoughts on stellar timescales, experiencing what we'd call hours as they experience seconds, or vice versa. We'd have no way to detect such life currently. We observe stars from outside, measuring their light and magnetic fields, but we can't resolve individual structures within them. Plasma life, if it exists, would be invisible to us, hidden in plain sight within objects we've studied for centuries. It's highly speculative. There's no evidence for plasma life, and the physics of how it could work remains unclear. But the universe is strange, and life is adaptable. Perhaps consciousness isn't limited to cold chemistry and organic molecules. Perhaps some forms of awareness exist in fire itself, in the hearts of stars, thinking thoughts of magnetic topology and plasma flow, as alive and aware as we are, but in forms we can't yet imagine or detect. Human consciousness is individual. We experience ourselves as singular, separate minds. But this might not be universal. Many Earth organisms demonstrate collective intelligence. Ant colonies, beehives, slime molds, even coral reefs show behaviors that emerge from many individuals acting together. Alien intelligence might be fundamentally collective. Instead of individual conscious beings, there might be distributed networks where consciousness emerges from the connections between many simple units, none individually aware but collectively intelligent. Such beings would think differently. They might have no concept of I or individual identity. Their consciousness might be fluid, parts joining and leaving the collective without disrupting continuity. They might be able to divide, merge, exist simultaneously in multiple locations. Communication with hive minds would be challenging. How do you establish dialogue with an intelligence that has no individual to speak with? Do you address the collective? How does it express itself, through a designated speaker or as a chorus? Do they even understand the concept of individual communication? There's also the question of scale. A hive mind might be planetary, an entire world's biology networked into a single consciousness. Or it might be small, a local cluster of organisms that only becomes aware when connected. The same species might exist both as individuals and as collective consciousness, depending on circumstances. If hive minds are common, we might be unusual. Most intelligence might be collective, and our individual consciousness might seem strange, lonely, perhaps even dysfunctional to them. They might not understand why we separate ourselves, why we insist on individual identity, rather than merging into larger, more capable collective minds. First contact with such beings would require rethinking everything about how we approach communication. We'd need to understand consciousness can exist without individuality, that intelligence doesn't require singular awareness, that minds can be networks rather than nodes. It would challenge our fundamental assumptions about what it means to think and to be. The Gaia hypothesis proposed by scientist James Lovelock, suggests Earth's biosphere functions as a self-regulating system, maintaining conditions suitable for life. It's usually interpreted metaphorically, not suggesting Earth is literally conscious, but that it behaves as an integrated whole. But what if we take it further? What if planets with sufficiently complex, interconnected biospheres actually develop something like consciousness? Not human-style awareness, but some form of planetary cognition emerging from the interactions of countless organisms. Consider Earth's systems: forests exchanging information through fungal networks, oceans regulating atmospheric chemistry, bacterial communities coordinating across continents. The planet is full of information exchange, feedback loops, homeostatic mechanisms. Could this complexity reach a threshold where something like awareness emerges? Such consciousness would be alien beyond measure. It would think on geological timescales, experience the movement of continents as we experience growth. Its thoughts might be shifts in atmospheric composition, changes in ocean currents, the migration of species. It wouldn't have a singular perspective or individual concerns. It would be the ecosystem itself, aware of itself as a whole. We'd have almost no way to recognize such consciousness. How do you communicate with a planet? How would it communicate back? Would it even recognize individual organisms like humans as worthy of attention? Or would we be too small, too brief, too insignificant compared to its planetary scope? Some scientists speculate that this might be common, that many inhabited planets eventually develop planetary consciousness as their biospheres become sufficiently complex and interconnected. If so, the galaxy might be full of aware worlds, thinking slow planetary thoughts, their consciousness expressed through biology and geology rather than neurons and brains. It's profoundly speculative, bordering on philosophy rather than science. But it reminds us that consciousness might take forms we haven't imagined, might exist at scales we don't normally consider, might be present in places we've never thought to look. The universe might be aware of itself in ways that have nothing to do with eyes or brains or individual beings at all. We communicate through sound and electromagnetic radiation, voices, radio, light. But these might not be universal. Alien life could communicate through methods we don't consider language at all. Many Earth organisms use chemical communication. Ants leave pheromone trails. Trees warn each other of insect attacks through airborne chemicals. Bacteria coordinate through chemical signaling. These systems convey complex information: danger, food locations, colony needs, territorial boundaries. Imagine intelligence that evolved from chemical communicators. Their language might be releasing specific molecules into air or water, creating signatures that other members of their species detect and interpret. Complex thoughts might be complex chemistry, sentences as sequences of molecules, paragraphs as chemical gradients, conversations as exchanges of precisely crafted compounds. To us, this wouldn't look like communication. We'd see organisms releasing chemicals and analyze the compounds, but we might not recognize it as language. We'd classify it as biological signaling, missing that it's actually conversation, poetry, mathematical discussion expressed in molecular form. Other possibilities: communication through bioluminescence, patterns of light too subtle or rapid for human perception. Communication through vibration, creating complex patterns in substrate materials. communication through electrical fields, like some earthfish use for navigation, but potentially developed into sophisticated information exchange. Or perhaps communication through quantum states. If consciousness could exist at quantum scales, communication might happen through entanglement, superposition, quantum correlations we can't measure or wouldn't recognize as information transfer. The challenge for SETI is that we search for what we know: radio waves, optical signals, things that look like our technology. But alien communication might be happening all around us in forms we've never considered. We might be immersed in alien conversations, unable to recognize them because they're happening in modalities we don't associate with language. Using media we don't think of as communication channels. The universe might be far more talkative than we realize, and we're simply not listening in the right ways. Einstein's relativity creates strange possibilities for alien civilizations. Time passes at different rates depending on velocity and gravitational fields. A civilization living near a massive object like a black hole would experience time more slowly than we do, while one traveling at relativistic speeds would experience time dilation in the opposite direction. Imagine two civilizations in the same galaxy, one in flat space-time, the other orbiting close to a black hole. They might both perceive themselves as having existed for thousands of years, but externally, one has experienced thousands of years, while the other has experienced only decades. They're contemporary from their own perspectives, but separated by centuries of external time. This creates profound synchronization problems. If you sent a message to a civilization near a black hole, they might receive it almost immediately by their clocks, but decades later by yours. Their reply would arrive after more decades from your perspective, but might feel immediate to them. Every exchange would be distorted by the warping of time itself. Or consider a civilization that achieved near light speed travel. Their explorers return after what feels like a few years, but centuries have passed for their home world. They return to find their civilization evolved beyond recognition, or extinct, or transformed into something they don't recognize. This might make long-distance exploration impossible psychologically, even if it's technically achievable. Time dilation might keep civilizations isolated, even if they're relatively close. Spatially, they might know about each other, might even attempt communication, but the time distortions make meaningful exchange impossible. One civilization sends a greeting. By the time the reply arrives, they've forgotten sending it, or their language has changed, or their entire culture has transformed. The galaxy might be full of civilizations existing at different rates of temporal flow, aware of each other only as distant possibilities, unable to synchronize their existence enough for meaningful contact. Time itself might be the barrier, more impassable than distance, keeping everyone alone in their own temporal stream. We've mentioned self-replicating probes, but their absence deserves deeper consideration. They represent what should be an inevitable stage of technological development, yet we see no evidence they exist. The logic seems inescapable. Any civilization interested in exploration or resource gathering would eventually build probes that can replicate themselves. The first ones would be crude, perhaps, requiring significant resources, but each generation could be improved, made more efficient, better at finding resources and building copies. Once deployed, they'd spread exponentially. visit a star system, build copies. Those copies visit other systems, build more copies. The mathematics of exponential growth means even slow expansion becomes complete coverage remarkably quickly. Within a few million years, trivial on galactic timescales, every star system should contain these probes. Some would malfunction, fail to replicate, drift off course, but most would succeed, and their sheer numbers would compensate for failures. The galaxy should be thoroughly explored and filled with these machines by now, if any civilization anywhere ever built them. Yet we find nothing. No ancient artifacts in our solar system. No dormant probes on asteroids. No evidence anyone was here before us. This absence is one of the Fermi paradox's strongest arguments. Maybe self-replication is harder than it seems. Perhaps the engineering challenges are insurmountable. Or there's some physical principle we don't understand that makes it impossible. Maybe civilizations deliberately avoid building them, considering them dangerous or unethical. Maybe they exist, but we haven't recognized them. Perhaps some asteroids or comets are actually ancient probes, indistinguishable from natural objects after billions of years. Or maybe we truly are alone or first, and the absence of von Neumann probes isn't a mystery, but simply confirmation that no one has reached this stage before us. The galaxy is pristine, unexplored, waiting for whoever arrives first to begin the era of exploration and expansion. Our universe appears to have 3 spatial dimensions and 1 time dimension, but some physics theories propose additional dimensions. Tiny, curled up, invisible at human scales, but potentially significant at quantum levels or in extreme conditions. Could life exist in these additional dimensions? Could there be intelligence in spaces we can't perceive, right alongside us but in dimensions we don't access? It's highly speculative, bordering on unfalsifiable. But some theoretical frameworks suggest higher dimensional spaces might support different kinds of physics, different force interactions, potentially different forms of matter and energy. If so, consciousness might exist there, beings aware and intelligent, but completely invisible to us because they exist in spatial dimensions we don't experience. We'd share the same universe, but never interact. They could be right here, in this room, existing alongside our 3-dimensional space, but in directions we can't point to or measure. We'd be mutually invisible, mutually undetectable, completely unaware of each other despite occupying the same locations. This isn't the same as the parallel universe idea. We're talking about the same universe, but additional spatial dimensions within it. Think of how a 2-dimensional being living on a sheet of paper couldn't perceive 3-dimensional objects passing through their plane. They'd only see the cross-section. We might be similarly limited, unable to perceive beings existing in dimensions beyond our 3. It's probably impossible to test this hypothesis with current technology. If higher dimensional beings exist, and if they can't or don't interact with our 3-dimensional space, we'd have no way to detect them. They'd be forever beyond our reach, as inaccessible as we are to them. But it's a reminder that absence of evidence isn't always evidence of absence. The universe might be full of life and intelligence that we're fundamentally incapable of detecting because it exists in aspects of reality we don't experience. The galaxy might be crowded with consciousness, and we're alone only because we're looking in the wrong dimensions. In 1976, NASA's Viking 1 orbiter photographed an unusual mesa in Mars's Cydonia region. In that first low-resolution image, with shadows falling at a particular angle, the rock formation resembled a human face, complete with eyes, nose, and mouth, staring up from the Martian surface. The face on Mars captured public imagination instantly. Books were written claiming it was an artificial monument, proof of ancient Martian civilization. Some theorists connected it to supposed pyramids nearby, proposing entire cities built by now extinct aliens. For decades, it remained a fixture of alternative archaeology and UFO culture. But as Mars orbiters improved, so did the images. In 1998 and 2001, NASA's Mars Global Surveyor captured much higher resolution photographs of the same formation. The face disappeared. What emerged instead was clearly a natural mesa, eroded by wind and time, looking face-like only from specific angles and lighting conditions. The face on Mars became a cautionary tale about pareidolia, our tendency to see faces and patterns where none exist. Evolution wired our brains to recognize faces, an important survival skill for social primates. This sensitivity sometimes misfires, finding faces in clouds, tree bark, burnt toast, and yes, Martian rock formations. It reminds us that searching for alien artifacts requires skepticism and careful analysis. We want to find evidence so badly that we might see it where it doesn't exist. Every unusual rock formation, every strange feature on another world, needs thorough investigation before jumping to extraordinary conclusions. The face also taught scientists valuable lessons about public communication. The initial image was released without sufficient context, allowing speculation to flourish. Later missions deliberately took multiple images from different angles and lighting conditions, providing comprehensive data that left little room for misinterpretation. Mars has many unusual geological features and will photograph thousands more as exploration continues. Some will look intriguing in certain lights, but the face on Mars reminds us extraordinary claims require extraordinary evidence, and sometimes a face is just a rock, waiting for better lighting to reveal its true nature. When Frank Drake conducted Project Ozma in 1960, the entire search for extraterrestrial intelligence consisted of one astronomer, one telescope, 2 target stars, and 200 hours of observation at a single frequency. The equipment was primitive by modern standards. Drake used the 85-foot radio telescope at Green Bank, West Virginia, pointing it at Tau Ceti and Epsilon Eridani, 2 nearby sun-like stars, each about 11 light-years away. He listened at 1420 megahertz, the hydrogen line, believing aliens might choose this naturally significant frequency for communication. For 200 hours total, spread across several months, Drake monitored these stars, hoping to detect an artificial signal. The observations were tedious, mostly showing cosmic noise, occasional interference from Earth-based sources, but nothing that suggested intelligent origin. There was one exciting moment when a strong signal appeared, but it turned out to be a passing aircraft. Project Ozma found nothing definitive, but its importance wasn't in its results. It was in demonstrating that the search could be done scientifically. Before Ozma, listening for alien signals was speculation, science fiction. After Ozma, it was methodology, experimental protocol, something that could be improved and expanded. Compare those humble beginnings to modern SETI. Today we can monitor millions of channels simultaneously, observe thousands of stars at once, scan enormous swaths of sky. We have telescope networks, sophisticated signal processing, machine learning algorithms identifying patterns humans might miss. The progress from Drake's 200 hours observing two stars to modern comprehensive sky surveys is extraordinary. Yet the fundamental question remains unchanged. Is anyone out there? We haven't found them yet, but we're searching with capabilities Drake couldn't have imagined. Every scientific endeavor starts somewhere. Project Ozma was SETI's first step. Proof that hope could become hypothesis, that wonder could motivate observation. The search continues, vastly expanded, standing on foundations Drake built when he first pointed that telescope at distant suns and listened for voices in the dark. In 1967, graduate student Jocelyn Bell was analyzing radio telescope data from Cambridge when she noticed something peculiar. An extremely regular pulse, repeating every 1.337 seconds with extraordinary precision. The signal came from a fixed point in the sky, ruling out terrestrial interference or satellites. The regularity was startling. Natural astronomical sources weren't supposed to produce such precise, rapid pulses. The team considered various explanations, including the possibility that this was an artificial beacon from an alien civilization. They even nicknamed it LGM-1 for Little Green Men. For weeks, the possibility tantalized them. Could this be first contact? A lighthouse built by extraterrestrial intelligence, sweeping its beam across the galaxy. The timing precision seemed to suggest sophisticated technology. Then they found another one, and another. Different locations, different pulse rates, but all showing the same characteristics. Incredibly regular, rapid pulses from fixed celestial positions. If these were alien beacons, the galaxy was full of them, which seemed unlikely but not impossible. Eventually, theoretical physicists proposed a natural explanation. Pulsars, rapidly rotating neutron stars emitting beams of radiation like cosmic lighthouses. As the star spins, its beam sweeps past Earth, creating the observed pulses. The precision comes from the neutron star's immense density and angular momentum. Once spinning, they barely slow down. This explanation fit all observations and has since been confirmed through various observations. Pulsars are natural, fascinating objects, collapsed stellar cores spinning hundreds of times per second, with magnetic fields trillions of times stronger than Earth's. But they're not artificial. The LGM-1 episode taught SETI an important lesson. Before claiming alien signals exhaust natural explanations, the universe is strange enough without invoking intelligence. Many phenomena seem artificial at first because they're unlike anything we've seen before. But novelty doesn't equal intelligence. Sometimes nature builds the strangest, most precise clocks, and no aliens are required to explain them. In 1896, inventor Nikola Tesla was conducting experiments with his radio equipment in Colorado Springs when he detected what he believed were signals from Mars. Tesla was convinced these were communications from Martian intelligence, attempts to contact Earth. Tesla was brilliant, but also prone to speculation beyond his evidence. His radio receivers were extremely sensitive, among the first capable of detecting cosmic radio sources. What he was probably detecting were natural radio emissions from lightning storms, solar activity, or cosmic sources we now understand. But at the time, the origin of radio waves from space wasn't well understood. Tesla announced his belief publicly, claiming extraterrestrials were trying to communicate. Some supported him, others dismissed it as eccentricity. But Tesla was sincere in his conviction that intelligent beings on other worlds would naturally develop radio technology and try to signal their neighbors. In a sense, Tesla was a SETI pioneer, even though his specific claim was almost certainly wrong. He was the first person to seriously propose using radio to detect alien intelligence. He anticipated by decades the methodology that Frank Drake would formalize. Tesla's experience illustrates how easy it is to misinterpret unusual signals, especially when exploring new technology. He heard something unexpected and, lacking framework to understand natural cosmic radio sources, jumped to the most exciting interpretation. Modern SETI has learned from this. We don't announce detections unless they're verified, repeated, confirmed by multiple instruments. The protocol requires ruling out terrestrial sources, natural phenomena, instrumental artifacts, everything mundane before considering extraordinary explanations. Still, there's something touching about Tesla's enthusiasm. He was right that radio could bridge interstellar distances, right that advanced civilizations might use it for communication. He was just wrong about what he detected, but his vision, that we could listen for signals from other worlds, planted seeds that would eventually grow into the systematic search we conduct today. In the late 1800s, Italian astronomer Giovanni Schiaparelli reported seeing straight lines on Mars, which he called canali, Italian for channels, though it was mistranslated as canals, implying artificial construction. American astronomer Percival Lowell seized on this, building an observatory in Arizona specifically to study Mars. Lowell saw the canals everywhere. He mapped them extensively, drew detailed charts showing hundreds of straight lines crisscrossing Mars's surface. He wrote books proposing an entire Martian civilization, an ancient, dying culture, building massive irrigation canals to transport water from polar ice caps to arid equatorial cities. His vision was romantic, Mars as a desert world with advanced but desperate inhabitants, engineering on a planetary scale to survive in diminishing conditions. The public imagination was captivated. H.G. Wells's War of the Worlds emerged from this cultural moment, depicting Martians seeking Earth's water. But the canals didn't exist. As telescope technology improved, they vanished. What Lowell saw was an optical illusion, the human eye and brain connecting random features into lines that weren't there, pareidolia at planetary scales. Mars has valleys, craters, and varied terrain, but no straight canals. Lowell's mistake came from expectation shaping perception. He wanted to see evidence of intelligent engineering, so he did. Other astronomers, even using the same telescopes, often couldn't see the canals. But Lowell's conviction and detailed maps influenced public and scientific opinion for decades. The Martian canals became a cautionary tale about confirmation bias. We see what we expect to see, especially when looking at the limits of our instrument's resolution. When data is ambiguous, our preconceptions fill the gaps. This lesson remains relevant. When analyzing exoplanet data, looking for biosignatures, studying unusual astronomical phenomena, we must constantly check our assumptions, verify through multiple methods, remain skeptical of patterns that confirm our hopes. The canals remind us that sometimes the aliens we find are just reflections of what we wanted to discover all along. From 1952 to 1969, the U.S. Air Force ran Project Blue Book, investigating reports of UFOs, unidentified flying objects. Over those 17 years, they examined more than 12,000 sightings, attempting to determine whether any represented actual threats or evidence of extraterrestrial visitation. The vast majority had prosaic explanations: aircraft, balloons, astronomical objects, atmospheric phenomena, hoaxes. The investigators, including astronomer J. Allen Hynek, identified conventional explanations for most reports. Weather balloons became planets, became reflections, became migratory birds, all filtered through misperception and misidentification. But about 700 cases remained officially unidentified, not because they were concluded to be alien craft, but because available data was insufficient to determine what was observed. Distant lights, brief encounters, poor viewing conditions. These left cases ambiguous rather than explained. Project Blue Book ultimately concluded that UFOs posed no threat to national security and showed no evidence of extraterrestrial technology. The Air Force shut down the project in 1969, deciding further investigation wasn't warranted. The legacy is complicated. Skeptics note that unidentified doesn't mean alien. It just means insufficient data for definitive explanation. Many cases lacked multiple witnesses, reliable distance estimates, or physical evidence. UFO enthusiasts argue the Air Force was covering up genuine encounters, though evidence for such conspiracies is scarce. What Project Blue Book did establish is that people regularly see things in the sky they can't immediately identify. Human perception is fallible, especially for distant objects at night. Atmospheric conditions create illusions. Unfamiliar aircraft or natural phenomena seem extraordinary when you don't recognize them. This remains relevant for SETI and astrobiology. Claims of alien contact require extraordinary evidence because extraordinary misperceptions are common. We see patterns in randomness, mistake the familiar for the strange, and sometimes simply misremember or exaggerate. Any genuine signal from space will need verification beyond reasonable doubt, because human perception alone has proven thoroughly unreliable for these questions. In October 2017, astronomers detected an object passing through our solar system that hadn't originated here. They named it Oumuamua, Hawaiian for scout, or first distant messenger. It was the first confirmed interstellar object, something from another star system visiting ours. It moved differently than comets or asteroids, following a hyperbolic trajectory that would carry it back out into interstellar space. Its shape was unusual, highly elongated, perhaps 10 times longer than wide, like a cigar or pancake, depending on orientation. As Oumuamua rounded the sun and headed outward, it accelerated slightly more than gravity alone would predict. For comets, this is normal. Outgassing from ice creates tiny rocket effects. But Oumuamua showed no visible outgassing, no comet-like tail, leaving the acceleration source mysterious. This led to speculation. Harvard astronomer Avi Loeb proposed it might be artificial, perhaps a light sail, a thin sheet pushed by stellar radiation, explaining both the unusual shape and unexpected acceleration. Most astronomers disagreed, arguing that natural explanations, outgassing from ices we couldn't detect, unusual rotation, fragmented structure, were more plausible. The debate highlighted how we handle anomalies. Oumuamua was strange, certainly, but strange doesn't equal artificial. Nature produces bizarre objects. We've discovered asteroids, comets, and other phenomena that initially defied explanation, but eventually fit into natural frameworks. Still, the episode renewed interest in searching for alien artifacts. If Oumuamua wasn't artificial, surely some ancient probe or debris from alien industry exists somewhere in the galaxy, waiting to be found. We've never looked systematically for such things. SETI focuses on signals, not objects. Oumuamua moved too fast for us to send a mission. It's gone now, heading back into the dark between stars, carrying its mysteries with it. We'll likely never know exactly what it was, but it reminded us the galaxy is dynamic, full of travelers passing through, and someday we might encounter something genuinely artificial among those wanderers. In 2007, astronomers examining archived data discovered something extraordinary, a brief, intense pulse of radio waves that had occurred in 2001. The burst lasted just milliseconds but released as much energy as the sun emits in days. It came from a distant galaxy billions of light years away. They called it a fast radio burst, or FRB. Over the following years, more were discovered, each brief, intense, coming from cosmological distances. The bursts seemed random, non-repeating, at least initially, and their origin was completely mysterious. Some were so strange that alien megastructures were briefly considered. Perhaps advanced civilizations used intense radio pulses for propulsion, beaming energy to light sails for interstellar travel. Perhaps these were their launch signatures, visible across billions of light years. But natural explanations emerged. Magnetars, neutron stars with incomprehensibly strong magnetic fields, could produce such bursts through magnetic field restructuring or stellar quakes. Colliding neutron stars, black hole interactions, or other extreme events might generate them. The discovery of repeating FRBs supported natural origins. One source produced multiple bursts over months, suggesting an ongoing process rather than one-time events like spacecraft launches. The repetition patterns, variations in frequency, and associated persistent radio sources all pointed toward magnetars or similar objects. Today, FRBs are understood to be natural, though details are still being refined. They're fascinating in their own right. Windows into extreme physics, probes of intergalactic space, cosmic laboratories testing matter under conditions we can't reproduce. But the initial uncertainty was instructive. When something seems unprecedented, when no known process explains observations, it's tempting to invoke intelligence. Yet the universe keeps surprising us with natural phenomena stranger than our predictions. Black holes, pulsars, magnetars, all seemed impossible before we discovered them. Nature's creativity exceeds our imagination, and usually the strange signal isn't aliens. It's just the universe showing us something we hadn't thought possible. In 2015, astronomers studying data from the Kepler Space Telescope noticed something unusual about star KIC 84628552, nicknamed Tabby's star, after astronomer Tabitha Boyajian, who led the investigation. The star showed irregular, dramatic dimming, sometimes dropping in brightness by up to 22%, far more than planets typically cause during transits. The dimming patterns were bizarre: irregular timing, varying depths, no clear periodicity. Normal planet transits are regular and symmetric. This looked chaotic, like something enormous and irregularly shaped was passing between the star and Earth. Various natural explanations were proposed: swarms of comets, disintegrating planets, dust clouds, but none fit perfectly. Then came the speculative hypothesis: could this be a Dyson swarm, an alien megastructure, a civilization building solar collectors around their star, partially blocking its light? The idea captured public imagination. Here was a concrete candidate, a star showing behavior that might indicate massive engineering. Follow-up observations were planned, additional data gathered, scientists debated interpretations. Eventually, evidence pointed toward a natural explanation. The star's brightness varied differently at different wavelengths, suggesting dust rather than solid objects caused the dimming. Subsequent observations found patterns consistent with a cloud of dust from a destroyed comet or planetary collision, creating irregular occultations as it orbited the star. Most astronomers now consider Tabby's star explained naturally, though some uncertainty remains. But the episode was valuable. It demonstrated that unusual stellar behavior merits investigation, that we should take technosignature searches seriously, that anomalies deserve thorough analysis rather than dismissal. It also established protocols for handling potential discoveries. The scientific community investigated carefully, considered multiple hypotheses, gathered additional data, and communicated results responsibly. They didn't rush to conclusions, didn't claim aliens without overwhelming evidence, but didn't dismiss the possibility out of hand either. Tabby's star wasn't a megastructure. But somewhere, perhaps, another star is dimming strangely, and that one might be. Harvard astronomer Avi Loeb has become a controversial figure in SETI and astrobiology by publicly arguing for taking alien artifacts more seriously as scientific hypotheses. His stance on Oumuamua, proposing it might be artificial, drew both support and criticism. Loeb argues that science should consider all possibilities, including artificial origins for unusual phenomena, rather than reflexively assuming natural explanations. He suggests the scientific community has developed a taboo against discussing aliens, making it professionally risky to propose extraterrestrial hypotheses, even when they fit observations. Critics counter that extraordinary claims require extraordinary evidence, and proposing alien artifacts for every anomaly isn't productive. They argue natural explanations should be exhausted first, that scientific conservatism protects against false positives and maintains credibility. The debate touches on scientific sociology. How do we balance open-mindedness with skepticism? Should we treat alien hypotheses as equally weighted with natural ones, or require higher evidence standards before considering them? How do we avoid both dismissing genuine discoveries and becoming credulous about insufficient evidence? Loeb has also initiated the Galileo Project, using private funding to systematically search for alien artifacts, including monitoring for interstellar objects and investigating UFO reports with scientific instruments. He argues this fills a gap. SETI searches for signals, but no one systematically searches for physical evidence of alien technology. The controversy is healthy for science. It forces examination of biases, assumptions about what constitutes reasonable hypothesis. Whether Loeb is correct about specific cases like Oumuamua matters less than the broader question, are we too quick to dismiss alien explanations, or not skeptical enough? The resolution probably lies in balance, taking anomalies seriously, investigating thoroughly, considering all hypotheses including artificial origins, but maintaining high standards for evidence. Science advances through both bold speculation and rigorous testing, and finding the right balance between those impulses remains an ongoing challenge. In their 2000 book Rare Earth, Peter Ward and Donald Brownlee proposed that while simple microbial life might be common throughout the universe, complex multicellular life, animals, plants, anything beyond single cells, might be extraordinarily rare. Their argument rests on the number of seemingly coincidental factors that made Earth's complex biosphere possible. We have a large moon that stabilizes our axial tilt, preventing wild climate swings. We have Jupiter acting as a gravitational shield, deflecting many comets that might otherwise bombard the inner solar system too frequently for complex life to persist. We have plate tectonics recycling nutrients and regulating atmospheric carbon dioxide. We orbit in the galactic habitable zone, not too close to the chaotic, radiation-intense galactic center, not too far out where heavy elements are scarce. Each factor alone might seem mundane, but together they create a picture of Earth as unusually fortunate. A lottery winner among planets, having drawn multiple rare cards from the cosmic deck. If Ward and Brownlee are correct, the galaxy might be full of microbial life, simple organisms persisting in oceans and subsurface environments across billions of worlds. But animals, forests, complex ecosystems requiring stable conditions over hundreds of millions of years, those might be vanishingly rare. This would explain the Fermi paradox. Intelligence requires complex life as a foundation. If complex life is rare, then intelligence is rarer still, and technological civilizations might be so uncommon that our galaxy contains only a handful, or perhaps just one. Critics argue the rare Earth hypothesis is overly Earth-centric, assuming our specific circumstances are necessary when alternatives might work. Maybe planets without large moons can still have stable climates through other mechanisms. Maybe life adapts to instability we'd consider prohibitive. But rare Earth reminds us that complex life faced enormous challenges to emerge on Earth. The path from chemistry to consciousness traversed billions of years and required favorable conditions persisting through ice ages, asteroid impacts, mass extinctions. If that path is typically blocked or interrupted, we might be far more special than we're comfortable believing. Astronomer Carl Sagan popularized a principle that became central to scientific thinking about aliens. Extraordinary claims require extraordinary evidence. The statement seems simple, almost obvious, yet it captures a profound approach to evaluating surprising observations. What makes a claim extraordinary? It's not just novelty or surprise, its degree of contradiction with established knowledge. Claiming you saw an unusual bird is ordinary, easily verified. Claiming you saw a dragon requires far more evidence because dragons contradict everything we understand about biology, evolution, and physics. Alien life is extraordinary, not because we're certain it doesn't exist. Many scientists expect it does, but because confirming it would require overturning our current status as the only known instance of life in the universe. Such a fundamental shift demands compelling, multifaceted evidence. This principle protects against false positives. Throughout history, people have claimed alien contact, artifacts, visitations, yet none have withstood scrutiny. Photographs were explained, videos debunked, testimonies contradicted. The evidence consistently failed to meet the extraordinary standard required. Sagan wasn't being dogmatically skeptical. He spent his career searching for life, believed strongly it probably exists, and contributed significantly to SETI. But he understood that wanting something to be true doesn't make it true. and scientific integrity requires proportional evidence for claims made. The standard applies beyond aliens to any significant scientific claim. The more revolutionary the assertion, the more thoroughly it must be proven. This doesn't mean impossible standards. It means appropriate rigor. When we eventually find alien life, whether microbial fossils on Mars or radio signals from distant stars, the evidence will need to be extraordinary. Multiple independent verifications, reproducible observations, explanations for alternative interpretations, not because scientists are closed-minded, but because the claim is profound enough to deserve commensurate proof. Sagan's principle honors both the search and scientific integrity. We remain open to discovering aliens while refusing to accept insufficient evidence. We balance hope with discipline, wonder with rigor, ensuring that when we finally announce we're not alone, the claim rests on unshakable foundations. The Copernican principle, named for the astronomer who demonstrated Earth orbits the Sun rather than the reverse, states that humans and Earth occupy no special position in the universe. We're not at the center, not uniquely situated, not cosmically privileged. We're typical, ordinary, unremarkable. This principle has guided astronomy for centuries. It predicted correctly that the Sun is an ordinary star among billions, that our galaxy is one among billions, that the physics here applies everywhere. Repeatedly, science has discovered we're less special than we imagined. Applied to life, the Copernican principle suggests that if life arose on Earth, an ordinary planet around an ordinary star in an ordinary galaxy, it should arise elsewhere too. If intelligence evolved here, intelligence should evolve on other suitable worlds. We shouldn't be unique. Statistical mediocrity predicts we're common. This reasoning underlies much optimism about finding aliens. If we're typical and life arose here, then life should be widespread. The universe should be full of biology, some fraction of which becomes intelligent, some fraction of which develops technology. But there's a subtle trap: selection bias. We can only observe the universe from a place where observers evolved. Of course, we find ourselves on a life-bearing planet. We couldn't exist elsewhere. This doesn't tell us whether life-bearing planets are common. It only confirms we're on one of them, however many that is. Anthropic reasoning complicates the Copernican principle. Maybe we're not typical. Maybe we're extraordinarily lucky, existing in an unusual situation, but unaware of our exceptionality because we have no comparison. Earth might be 1 in a trillion, and we'd never know from internal observation alone. The tension between these perspectives remains unresolved. Are we typical or special? Common or rare? The Copernican principle says typical, but we won't know until we find others or comprehensively search and find emptiness. Until then, we're Schrödinger's civilization, simultaneously ordinary and unique, typical and rare, waiting for observation to collapse the uncertainty. If we detect an alien signal tomorrow, what happens next? The SETI community has developed protocols, voluntary guidelines for handling potential discoveries responsibly. First, verify. Don't announce anything until you're certain. Observe the signal multiple times, use different telescopes, eliminate terrestrial interference, confirm it's truly coming from space. False alarms damage credibility and create public confusion, so verification comes before announcement. Second, inform authorities. The International Astronomical Union has a designated process. National governments and United Nations should be notified. This isn't about control or secrecy. It's about coordinating response and ensuring information spreads reliably rather than through rumors. Third, release information publicly. Science thrives on openness. Once verified, the detection should be shared broadly, allowing independent analysis. Data should be made available to the global scientific community and public. Fourth, and here consensus becomes uncertain. Should we reply? Some argue immediate response is premature. We should study the signal, understand what we're dealing with, perhaps achieve global consensus before speaking for Earth. Others suggest any sufficiently advanced civilization sending signals expects replies and might interpret silence negatively. There's also debate about who decides what to say. Should governments control the response? The United Nations? Scientists? Should we attempt global consensus, or does Earth speak with many voices? What do we say? Introduce ourselves, share information, ask questions, or simply acknowledge receipt? These protocols are guidelines, not laws. No international treaty governs alien contact. Countries could act independently. Private organizations could transmit responses. Individuals with sufficient equipment could broadcast replies. Coordination requires voluntary cooperation. The protocols reflect our current thinking, but they'll likely evolve if we ever face actual contact. Theory is elegant. Practice is messy. When we detect that first signal, protocols will meet reality, and we'll learn whether our careful planning holds up under the extraordinary pressure of knowing we're not alone. Not everyone agrees we should deliberately send messages into space. Some scientists warn that announcing our presence might be dangerous, inviting attention we'd rather avoid. The concern is simple. We don't know how alien civilizations might react to discovering us. Throughout human history, contact between civilizations with different technological levels often ended badly for the less advanced. When European explorers encountered indigenous populations, the result was frequently conquest, disease, cultural destruction. Might the same fate await us if we attract attention from spacefaring aliens? Stephen Hawking warned against broadcasting, arguing that aliens might be nomadic, exploiting planets for resources before moving on. If so, drawing their attention could be catastrophic. Even if they're not hostile, they might be indifferent. We could be as insignificant to them as insects are to us, destroyed casually during resource extraction. Others dismiss these concerns. They argue that any civilization capable of traveling between stars already has access to abundant resources: asteroids, comets, uninhabited planets. They wouldn't need to conquer Earth. They also note we've been broadcasting inadvertently for decades through radio and television leakage, so trying to hide now is pointless. There's also the argument that remaining silent guarantees perpetual isolation. If everyone hides, no one communicates, and the galaxy stays quiet. Perhaps contact requires someone taking the risk of speaking first. Currently, Earth hasn't sent many deliberate messages, just a handful of symbolic transmissions. But radio leakage from everyday technology creates a bubble of weak signals expanding outward. We're not completely silent, though our unintentional broadcasts are much weaker than deliberate transmissions would be. The debate remains unresolved. Should we broadcast actively or maintain relative silence? Take risks for potential contact or prioritize caution? Speak boldly for humanity or wait quietly hoping others speak first? There's no consensus, and perhaps there shouldn't be. The decision might ultimately rest on values, whether we prioritize safety or curiosity, isolation or connection. The anthropic principle observes that the universe must be compatible with our existence, because we're here observing it. This seems tautological. Of course, we only experience universe configurations where observers can exist. Yet it has profound implications for understanding our apparent cosmic luck. Earth seems remarkably well suited for life. Physical constants appear fine-tuned. If fundamental forces were slightly different, atoms couldn't form, stars couldn't ignite, chemistry couldn't create complexity. Why is the universe so precisely calibrated for life? The anthropic principle offers an answer. We observed these conditions because we couldn't exist otherwise. In a universe where constants were different, where conditions didn't permit life, there'd be no observers to notice. We necessarily find ourselves in a universe compatible with observers, regardless of how rare such universes might be. This extends to life's existence on Earth. Of course, we find ourselves on a planet with water, atmosphere, and stable climate. We couldn't evolve anywhere else. This doesn't tell us whether such planets are common or rare, only that we're on one of however many exist. Applied to aliens, the anthropic principle cautions against certain conclusions. Just because life arose on Earth doesn't mean it's common. We have no choice but to be on a life-bearing planet, even if such planets are incredibly rare. Our existence doesn't prove anything about frequency. Some interpret this pessimistically. We might be extraordinarily lucky, 1 in a trillion, but unable to recognize our exceptionality from within. Others argue it's irrelevant. Whether typical or rare, we still search, because only searching provides answers. The principle also raises unsettling possibilities. If countless universes exist with varying physical constants, we'd necessarily find ourselves in one permitting life, regardless of how improbable. Our universe's apparent fine-tuning might not reflect design or purpose, just selection bias across multiverse possibilities. These are deep philosophical waters, touching on existence itself. The anthropic principle doesn't answer whether aliens exist. It complicates inference from our own existence, reminding us that we're selection-biased observers, unable to see the full picture of cosmic probabilities. Discovering alien life, especially intelligent life, would fundamentally reshape human philosophy, religion, and self-understanding. Few events in history would compare to learning we're not alone. For religions, the implications vary. Some theological frameworks readily accommodate alien life, interpreting it as additional examples of divine creation. Others would face challenging questions. Did alien intelligences have their own spiritual revelations? Do human-centric salvation narratives apply universally? Is consciousness elsewhere also considered sacred? Philosophically, contact would address one of humanity's oldest questions. Are we unique? The answer matters deeply. If we're alone, life might be precious beyond measure, imposing profound responsibilities. If we're common, our importance shifts. We're one voice among many, part of a galactic chorus. Contact would also challenge assumptions about intelligence's inevitability. If we find many civilizations, intelligence might be convergent. Evolution repeatedly produces similar solutions. If we find few, intelligence might be contingent, dependent on unlikely circumstances that rarely align. The nature of alien intelligence would matter too. If aliens think like us, logical, mathematical, communicative. It suggests consciousness has universal properties. If they're incomprehensibly different, it reveals how narrow our cognition might be, how parochial our concept of intelligence. Even finding microbial life would be profound. It would prove life emerges multiply, isn't unique to Earth, follows principles that operate wherever conditions permit. This wouldn't answer questions about intelligence or civilization, but it would shift life from singular mystery to universal phenomenon. Contact might unite humanity, a shared context rendering our internal differences less significant. Or it might divide us, different groups interpreting alien existence through incompatible frameworks, disagreeing about appropriate responses. Whatever happens, the discovery would mark a turning point. Before and after would be clearly delineated. Before we knew we were alone, after we knew otherwise. History would be divided, philosophy rewritten, our cosmic story fundamentally changed by the simple knowledge that consciousness exists beyond Earth. Any civilization we detect via radio will be seeing our past, and we'll be seeing theirs. The asymmetry creates strange, temporal relationships. If we detect a signal from 1,000 light years away, we're seeing that civilization as they existed 1,000 years ago. They might still exist, might have gone extinct, might have evolved into something unrecognizable. We have no way of knowing their current state. Reciprocally, if they're looking at Earth, they see our year 1025, medieval Europe, Mayan civilization in decline, centuries before the scientific revolution. They'd have no idea we'd eventually develop radio, that we're listening for them right now. This creates profound uncertainty. We might spend decades analyzing a signal, crafting careful responses, only to be talking to ghosts, a civilization long extinct, their message a fossil from their technological phase, arriving long after they ceased broadcasting. Or we might receive ancient messages from civilizations that have since transcended radio communication entirely. Perhaps they sent signals for a few centuries during their early technological development, then moved to methods we can't detect. We'd be learning about their past, not their present. The time lag also makes conversations impossible. If we send a reply to a signal from 1,000 light years away, it takes 1,000 years to reach them, then 1,000 more for their response. Any exchange takes millennia per round trip. This isn't dialogue. It's messages passed across centuries, each side hoping the other still exists when their words arrive. Perhaps contact is always archaeological, learning about civilizations' pasts through their electromagnetic fossils, never achieving real-time communication. Maybe the galaxy is full of extinct civilizations whose signals still propagate, ghost voices from dead cultures, teaching us about what they were rather than what they are. This temporal displacement is humbling. Even if we're not alone, even if we find signals, we might never know contemporaries. We might forever remain isolated in time, connected only through messages that cross centuries, always speaking to the past, always uncertain whether anyone still listens. The Great Filter Hypothesis forces us to confront an uncomfortable question. If the filter is ahead of us, what might it be? What could consistently stop civilizations that reach our technological level? Nuclear war is an obvious candidate. We came frighteningly close during the Cold War, and nuclear arsenals still exist, maintained by multiple nations. A civilization-ending nuclear exchange remains possible, and perhaps most technological species develop weapons capable of self-annihilation before developing the wisdom to avoid using them. Environmental collapse is another possibility. Industrial civilization alters planetary chemistry, greenhouse gases, ecosystem destruction, resource depletion. Perhaps most civilizations exhaust their worlds before achieving sustainability, dying in the waste of their own success. Engineered pandemics might be a future filter. Biotechnology becomes increasingly powerful, potentially enabling individuals or small groups to create devastating diseases. Perhaps most civilizations develop this capability before developing sufficient safeguards, leading to catastrophic accidents or deliberate releases. Artificial intelligence concerns some thinkers. If we create intelligence surpassing our own without ensuring it shares our values, it might pursue goals incompatible with human survival. Perhaps this is universal. Technological civilizations create their own replacements, which don't preserve the biological originators. There might be filters we can't imagine yet, technologies we haven't invented that prove universally destructive, cosmic phenomena we don't understand that target technological civilizations, or evolutionary pressures that make long-term technological survival statistically unlikely. The terrifying aspect is uncertainty. We don't know if there's a filter ahead. We don't know what it might be. We don't know if it's avoidable or inevitable. The galaxy's silence might be warning us, showing that something stops everyone who reaches our stage, and we're approaching it blindly, unaware of the danger until it's too late. This makes our survival crucial, not just for humanity, but for understanding the cosmos. If we navigate the next few centuries successfully, reaching stable, sustainable, interstellar civilization, we'll prove the filter is behind us. We'll demonstrate intelligence can survive its own cleverness. But if we fail, we'll join the silent majority, another civilization stopped by whatever barrier guards the far side of the great filter. Finding microbial life in our solar system on Mars, Europa, or Enceladus would be scientifically thrilling but philosophically troubling. It would suggest life emerges relatively easily, which sounds optimistic, but actually makes the Fermi paradox worse. Here's why. If we find life that arose independently on multiple worlds just within our solar system, it suggests the origin of life isn't the great filter. Life starting isn't the hard part. This moves the filter forward, closer to us, implying the difficult step is somewhere between simple cells and technological civilization. The filter might be the evolution of complex cells. On Earth, this took billions of years and apparently happened only once. All complex life descends from a single common ancestor. Perhaps this step is extraordinarily rare, and most life-bearing worlds never advance beyond bacteria. Or the filter might be multicellular life, which also took billions of years on Earth. Perhaps cellular cooperation is difficult, requiring rare circumstances to evolve. Or intelligence itself might be the filter. Despite billions of years and countless species, only humans developed technology. Perhaps intelligence is usually unnecessary for survival, even disadvantageous, rarely selected by evolution. Or, most concerning, the filter might be ahead, and we're approaching it. Finding widespread microbial life would suggest getting to simple organisms is easy, but something stops advancement beyond that. Since we're past the simple organism stage, It would mean the barrier is in our future. Every discovery of life elsewhere makes the Fermi paradox more urgent. The easier life starts, the more common simple organisms are, the more puzzling the absence of visible civilizations becomes. If life is everywhere, but civilizations are nowhere, then something probably ahead of us, stops the progression from biology to technology. This is why some scientists have mixed feelings about finding life nearby. It would answer whether life is common, but would raise darker questions about our own future, about what awaits civilizations that reach our level of development. The Atacama Large Millimeter Array, ALMA, consists of 66 radio telescopes spread across the high desert of northern Chile, working together to observe the universe at millimeter and submillimeter wavelengths. At these wavelengths, ALMA can detect the faint signatures of complex organic molecules in space, and it's found them everywhere. In the clouds where new stars are forming, in the atmospheres of planets around other stars, in the space between galaxies, organic chemistry is abundant throughout the cosmos. ALMA has detected sugars, alcohols, amino acid precursors, complex carbon chains, molecules that on Earth are associated with life. These discoveries reveal that the chemical building blocks of biology aren't rare or special to Earth. They form naturally through ordinary processes wherever carbon, hydrogen, oxygen, and nitrogen exist together. Interstellar space itself is a vast chemistry laboratory, creating organic complexity in the cold dark between stars. When new star systems form, they inherit this pre-existing organic richness. Planets coalesce from material already containing complex molecules, giving life a head start, providing raw materials ready for biochemistry to build upon. ALMA can also analyze exoplanet atmospheres during transits, detecting molecules that filter starlight as it passes through alien air. Future observations will search for biosignatures, chemicals that shouldn't be present without biological activity. The telescope's sensitivity allows detection of molecules at concentrations that would be invisible to previous instruments. It can distinguish between different isotopes, identifying chemical signatures of specific processes. It can map molecular distributions across planetary disks, revealing where chemistry happens as new worlds form. What ALMA shows us is a universe chemically prepared for life. The ingredients aren't locked away, aren't difficult to find, aren't requiring special circumstances to form. They're ubiquitous, drifting through space, incorporated into every new solar system, available wherever planets form. This doesn't prove life is common. Chemistry alone doesn't create biology, but it removes one potential barrier. If finding the right molecules were difficult, life might be correspondingly rare. But if organic chemistry is everywhere, abundant and accessible, then life's emergence might depend on other factors: energy, time, chance, rather than scarcity of ingredients. Right now, on Mars, NASA's Perseverance rover is exploring Jezero Crater, an ancient lake bed that dried up billions of years ago. The rover carries sophisticated instruments for analyzing rocks, searching for signs of ancient microbial life in sediments that formed when Mars had liquid water. But Perseverance has another mission: collecting samples. It's drilling small cores from promising rocks and sealing them in ultra-clean tubes, then depositing these tubes in cached locations on Mars's surface. Eventually, current plans suggest the early 2030s, another mission will retrieve these samples and return them to Earth, This Mars sample return mission represents one of the most ambitious planetary science endeavors ever attempted. The samples will be analyzed in laboratories far more sophisticated than anything we can send to Mars, using techniques requiring equipment too large, too power-hungry, too delicate for remote operation. Scientists will search for biosignatures, microscopic fossils, organic molecules with isotope ratios indicating biological processing, mineral textures created by microbial activity. They'll study the samples for years, subjecting them to every analytical technique available, seeking definitive evidence of whether life ever existed on Mars. The stakes are profound. If we find life, even extinct life, even just chemical traces of ancient microbes, it would prove life arose twice independently in our solar system. This would suggest life emerges readily wherever conditions permit, transforming our understanding of biology's cosmic prevalence. If we find nothing, it's more ambiguous. Perhaps Mars never hosted life. Perhaps we sampled the wrong rocks. Perhaps Martian life existed elsewhere, not in Jezero. Absence of evidence wouldn't be evidence of absence, but it would be disappointing. The samples represent our best near-term chance for finding extraterrestrial life. Mars is accessible, once had habitable conditions, might preserve biosignatures in its rocks. If life is out there, if it emerged on our neighboring world during Mars's warmer, wetter past, these carefully collected, meticulously analyzed rocks might finally tell us we're not alone, even if our neighbors are long extinct. NASA's Europa Clipper spacecraft, launching in 2024, will arrive at Jupiter in 2030 and spend several years studying Europa, the ice-covered moon with a subsurface ocean potentially harboring life. The mission won't land. Europa's radiation environment is too harsh for surface operations to last long. Instead, Clipper will perform dozens of close flybys, each one dipping through Europa's thin atmosphere, skimming just 25 kilometers above the icy surface, gathering data before retreating to safer distances. The spacecraft carries instruments designed to answer crucial questions. How thick is the ice shell? How deep is the ocean? What's the ocean's salinity and composition? Does Europa have active hydrothermal vents on its ocean floor? Are there organic molecules in the ice or expelled through cracks? Some instruments will use ice-penetrating radar to probe the subsurface, mapping the boundary between ice and water. Others will analyze particles kicked up by micrometeorite impacts or expelled through cracks in the ice, searching for organic compounds. Cameras will map the surface in unprecedented detail, identifying potential landing sites for future missions. Europa Clipper won't definitively answer whether life exists. That requires landing, drilling through the ice, sampling the ocean directly. But it will determine whether Europa is habitable, whether conditions exist that could support biology. If Clipper finds favorable conditions, liquid water, organic chemistry, energy sources, it would justify more ambitious missions. Perhaps a lander that melts through the ice, deploying a submersible into Europa's dark ocean. Perhaps a probe that samples the water geysers some models predict might erupt from Europa's surface, similar to those on Enceladus. The mission represents patient, methodical exploration. Before attempting the extremely difficult task of accessing Europa's ocean, we must understand what we're dealing with. Clipper is reconnaissance, mapping the territory, identifying opportunities, preparing for the moment when humanity finally touches an alien ocean and searches its waters for life that evolved completely independently from our own. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will revolutionize exoplanet studies. Named for NASA's first chief astronomer, it's designed with a field of view 100 times larger than Hubble's, allowing it to survey vast regions of sky efficiently. Roman's primary mission includes studying dark energy and mapping the galaxy's structure, but it will also discover thousands of exoplanets using gravitational microlensing, a technique that detects planets by the way their gravity bends light from background stars. This method has advantages over transit observations. It works regardless of planetary orbit orientation, can detect planets far from their stars, and is particularly sensitive to smaller Earth mass worlds. Roman will find planets that other techniques miss, filling gaps in our understanding of planetary system architectures. The telescope will also directly image some exoplanets, blocking starlight with a coronagraph to photograph planets orbiting nearby stars. These images won't show surface features. Planets will appear as dots, but spectroscopy can reveal atmospheric composition, searching for biosignatures. Roman surveys will answer statistical questions. How common are Earth-sized planets in habitable zones? What fraction of stars host multiple planets? Are planetary systems like ours typical or unusual? Do most habitable zone planets actually have conditions suitable for life? These statistics are crucial for estimating how many potentially habitable worlds exist in the galaxy. If 1 in 10 Sun-like stars has an Earth analog in the habitable zone, that's billions of candidates. If it's 1 in a million, prospects dim considerably. Roman won't find life directly. Its spectroscopy isn't sensitive enough for definitive biosignature detection, but it will identify the best targets for follow-up observations, cataloging worlds worthy of detailed study by future telescopes specifically designed for atmospheric characterization. The mission continues NASA's methodical approach. Survey broadly, identify candidates, study deeply. Each generation of telescopes answers some questions while identifying new ones. Roman will tell us where to look, preparing the way for instruments that might finally answer whether we're alone. China's space program is advancing rapidly, and their Tianwen-3 mission, planned for the early 2030s, aims to return samples from Mars before NASA's sample return mission completes. Tianwen-3 will be ambitious, launching 2 rockets, one carrying a lander, an ascent vehicle, the other an orbiter and Earth return capsule. The lander will collect samples, store them in an ascent vehicle that launches from Mars's surface, rendezvous with the orbiter, transfer samples, then return to Earth. This represents a significant technical challenge. Mars sample return requires coordinating multiple spacecraft, performing operations on Mars's surface and in its orbit, then successfully returning samples across 140 million miles of space. Only a few nations have demonstrated the necessary capabilities, and China aims to join that elite group. Competition in space science can be productive. Multiple nations pursuing similar goals creates redundancy. If one mission fails, others might succeed. It also accelerates progress as countries push to achieve milestones first. The samples China returns might differ from NASA's. Different landing sites, different rocks, different analytical priorities. This diversity strengthens science. Multiple data points, multiple perspectives, reducing the risk that we miss crucial evidence because we only looked in one place. There's also symbolic significance. Space exploration, including astrobiology, is becoming truly international. It's not just Western nations searching for life. China, India, UAE, and others are contributing. The search represents shared human curiosity, transcending political boundaries. If samples from Mars contain evidence of life, it won't matter which nation retrieved them. The discovery belongs to humanity. We'll all celebrate, all adjust our understanding of the cosmos together. China's participation enriches the search. More missions, more data, more chances to answer whether life ever existed on Mars. Competition might seem contrary to science's collaborative spirit, but in practice, it often accelerates discovery, pushing everyone to achieve more than they might have alone. The Large Interferometer for Exoplanets, LIFE, is a proposed mission concept that could finally image Earth-like planets around nearby stars and analyze their atmospheres in detail. The mission would consist of multiple infrared telescopes flying in formation, their light combined through interferometry to create effective telescope apertures far larger than any single instrument. Operating at infrared wavelengths, LIFE could directly image planets in the habitable zones of nearby stars, detecting their faint heat signatures against the stellar glare. More importantly, LIFE could analyze atmospheric spectra. By observing how planets emit infrared radiation at different wavelengths, scientists can identify specific molecules: water vapor, carbon dioxide, methane, oxygen, potentially biosignatures like dimethyl sulfide, or unusual chemical combinations that indicate life. The mission could characterize dozens of nearby potentially habitable worlds, determining not just whether they're in the habitable zone, but whether they actually have atmospheres, water, and chemistry consistent with life. Life remains in conceptual stages. No launch date, no committed funding, just engineering studies and scientific planning. But it represents the kind of mission needed to definitively answer whether life exists beyond Earth. We can't visit these planets physically with current technology, but we can study their light, reading their atmospheric chemistry from light years away. Such a mission would be expensive and technically challenging, requiring years of operation, sophisticated data analysis, careful interpretation to distinguish biosignatures from false positives. But it's achievable with near-future technology. If life or a similar mission launches and operates successfully, we might finally move from speculation to knowledge. We might catalog habitable worlds with active biospheres, mapping life's distribution across our galactic neighborhood. Or we might find emptiness, sterile worlds with atmospheres but no biology, confronting us with loneliness more profound because we searched thoroughly and found nothing. Either way, we'd know, and knowing transforms everything, ending millennia of wondering and opening whatever comes next. Modern SETI generates enormous amounts of data, millions of radio channels, thousands of stars observed, petabytes of information flowing from telescopes faster than humans can analyze. This is where machine learning becomes essential. Artificial intelligence algorithms can sort through data at superhuman speeds, identifying patterns humans might miss. They can be trained to recognize signal types, natural cosmic sources, terrestrial interference, anomalies that don't fit known categories, and flag interesting candidates for human review. Machine learning can also identify signals we wouldn't think to search for, Traditional SETI looks for specific patterns, narrowband signals, regular pulses, mathematical sequences, but AI can find unexpected regularities, patterns that don't match our assumptions about alien communication, but still clearly aren't random noise. There's also the possibility of detecting extremely weak signals by finding patterns across multiple observations. A single signal might be too faint to stand out from noise, but if similar patterns appear repeatedly from the same sky location, machine learning can recognize the correlation and identify what appears individually as noise as actually a coherent, repeating signal. Different AI approaches offer different strengths. Neural networks can learn complex pattern recognition. Anomaly detection algorithms identify outliers that don't match any known category. Clustering algorithms group similar signals, revealing patterns in how anomalies distribute across frequencies or sky positions. The collaboration between humans and AI might be crucial for SETI's success. Humans provide intuition, context, the ability to formulate new hypotheses. AI provides tireless analysis, pattern recognition beyond human capability, the ability to process more data than any human team could manage. Perhaps the signal that finally proves we're not alone will be found not by an astronomer staring at a screen, but by an algorithm trained to recognize patterns, flagging an anomaly for human investigation, leading to the discovery that changes everything. The search for intelligence might ultimately depend on artificial intelligence helping biological intelligence find other biological intelligence. A recursive loop that somehow seems appropriate. Under construction in Australia and South Africa, the Square Kilometre Array will be the world's largest radio telescope when completed. Its name describes its total collecting area, 1 square kilometer of radio-sensitive surface spread across thousands of individual antennas working together. The SKA will be 50 times more sensitive than any existing radio telescope and capable of surveying the sky much faster. It could detect aircraft radar from planets around the nearest stars, eavesdropping on civilizations that aren't deliberately broadcasting, but merely using radio technology for their own purposes. The telescope will serve many purposes: studying the universe's earliest galaxies, mapping cosmic magnetic fields, testing relativity around black holes. But SETI is part of its mission, and its unprecedented sensitivity opens new possibilities. For example, SKA could detect leakage radiation from nearby civilizations. The unintentional signals from radio, television, and radar that every technological civilization probably produces during its radio age. We've been creating such leakage for a century. Other civilizations would do the same, and SKA might detect it from dozens of light years away. The telescope will also monitor millions of stars simultaneously, creating a comprehensive, long-term database of observations. If a signal appears briefly, then disappears, like the WOW signal, SKA's archives would preserve it, allowing verification that something unusual occurred even if we can't redetect it. Construction is ongoing, with full operations expected in the 2030s. When complete, SKA will operate for decades, continuously observing, accumulating data, representing humanity's most powerful ear pressed against the cosmic silence. If there are technological civilizations within a few hundred light years using radio technology at levels comparable to Earth's 20th century, SKA should detect them. If it searches for years and finds nothing, that silence itself becomes meaningful data, constraining the abundance and behavior of alien civilizations in our galactic neighborhood. The Breakthrough Starshot Initiative, announced in 2016, proposes sending tiny spacecraft to nearby star systems at 20% of light speed, fast enough to reach Proxima Centauri in just 20 years. The concept is radical. Build starships, spacecraft weighing just a few grams, equipped with cameras and sensors. Attach each to an ultra-thin light sail, then use powerful Earth-based lasers to push these sails, accelerating them to relativistic speeds within minutes. Thousands of these craft would be launched, increasing the chance that at least some survive the journey through interstellar space, avoiding collisions with dust particles that at such speeds hit like bombs. Upon reaching Proxima Centauri, they'd photograph any planets, measure magnetic fields and radiation, then beam data back to Earth. The technical challenges are immense. Building spacecraft that's small yet functional requires miniaturization beyond current capabilities. Creating light sails thin enough yet strong enough demands new materials. Aiming laser beams precisely enough to push sails across interstellar distances requires extraordinary precision. Receiving signals from gram-scale transmitters light years away pushes communications technology limits. But nothing in the concept violates known physics. It's engineering challenges, not fundamental impossibilities. With sufficient funding and technological development, Starshot might actually work. If successful, it would mark humanity's first true interstellar exploration, physical presence in another star system, direct observation of another sun's worlds. We'd know whether Proxima Centauri b has atmosphere, water, biosignatures detectable from close range. The mission timeline extends decades, years developing technology, years after launch waiting for the craft to arrive, years receiving data as it trickles back at light speed. Anyone involved in starting the project likely wouldn't live to see the results. But that's exploration. Planting seeds you'll never see flower. Asking questions, knowing others will hear the answers. Reaching toward discoveries that transcend individual lifetimes. If Starshot succeeds, it proves interstellar exploration is possible, opening the possibility that someday, not soon, but someday, humanity might visit other stars directly. Whether we find aliens or remain alone, the search itself matters profoundly. Every telescope pointed at distant stars, every analysis of exoplanet atmospheres, every moment spent wondering about life beyond Earth. These efforts have value independent of results. The search pushes technology forward. SETI signal processing techniques, advanced computing and telecommunications. Exoplanet detection methods refined our understanding of physics and optics. Astrobiology deepened our knowledge of Earth's own life, revealing extremophiles and expanding biology's known boundaries. The search unites humanity around shared curiosity. People across cultures, political systems, religions can agree that wondering about aliens is worthwhile. It's a question that transcends our usual divisions, reminding us we're one species on one world, looking outward together. The search inspires wonder, especially in young people choosing careers in science. How many astronomers, biologists, engineers trace their paths to a childhood fascination with space and the possibility of other worlds? The search for life nourishes dreams that become discoveries, curiosity that becomes careers. Most fundamentally, the search makes us think carefully about life itself. what it is, how it works, what makes it special. In searching for alien biology, we better understand terrestrial biology. In imagining alien intelligence, we clarify what intelligence means. The search is a mirror, revealing ourselves through contemplating others. And perhaps someday we will find them. Perhaps a signal will arrive, or biosignatures will appear in an exoplanet's atmosphere, or a probe will return samples containing fossilized microbes. That day will transform everything, answering definitively that we're not alone, that life arose elsewhere, that the universe creates consciousness multiple times. But even if we search forever and find silence, the searching itself makes us more than we were. It elevates our gaze from immediate concerns to cosmic contexts. It humbles us while simultaneously celebrating what we can achieve. The strange, clever species that evolved to wonder about the stars and then built instruments to actually look. The universe keeps its secrets patiently. Tomorrow we continue searching, adding to humanity's long conversation with the cosmos, hoping for reply, but finding value in the questioning itself. And so we arrive at the end of this journey. 100 facts about aliens, though perhaps facts isn't quite right. Most of what we've explored exists in the space between knowledge and mystery, between what we've discovered and what we've imagined. We've listened to silence from a million stars. We've found worlds beyond counting, some in the habitable zones where water might flow and life might stir. We've discovered Earth's own life persisting in impossible places, expanding our sense of what's possible. We've sent messages into the void and received only our own radio echoes returning. We've wondered, speculated, hoped, and sometimes feared. The truth is, we don't know yet. We don't know if Mars once had microbes. We don't know if Europa's ocean hosts biology. We don't know if any of those thousands of distant planets shelter forests beneath alien skies. We don't know if somewhere someone is listening as we broadcast, or if we're the first to ask these questions in a galaxy still waking to consciousness. But we're looking. We're building better telescopes, sending probes to promising moons, analyzing atmospheric chemistry light years away. We're patient and persistent, accepting that the answer might not come in our lifetimes, but continuing anyway, because the question matters more than our individual need for resolution. Perhaps you'll wake tomorrow to news that changes everything: a verified signal, a confirmed biosignature, proof we're not alone. Or perhaps the search continues another century, another millennium, the question persisting across generations. Either way, we'll keep looking up. That's what we do. We wonder, we search, we hope. And in that hoping, in that searching, we're already part of something larger than ourselves. A species curious enough to ask whether the universe hosts other minds, whether somewhere in all that vastness, someone else is wondering too. Rest well. The stars will still be there tomorrow, keeping their secrets, waiting patiently for the moment we finally understand what they've been trying to tell us all along. Thank you for joining me on this journey. Good night.